Hello, I'm still audible, right?
Yes.
I think I started recording. Can you just confirm it?
Yeah, it's recording.
Okay, maybe you can start. I think 10 people are here. Maybe more people will join as we progress. So, hi everyone. Good evening. I am Prashok Shankar. I am a fourth year PhD student in the Department of ECE. So today I will be having a discussion about transform theory, mainly on Fourier transform, Laplace transform, and set transform, and how the questions will be there for the interview. Maybe we can have a quick introduction. So, like I told, I'm Prashab, and I did my BTech from NIT Calicut in the year 2019. And then I joined here as a direct PhD candidate. And I'm working with Professor Sandeep, and my area of research is wireless communication. Maybe Nitin, can you introduce yourself?
Yeah, thanks, Prashok. I'm Nitin. I'm a third year PhD student here. Uh, my background is I did my BTech in in 2019 to 2015 to 2019, and then later joined for MTech in IASc in 2020, and later I converted to PhD. My main area of research is in image processing, and my research advisor is Professor Rajiv Soundararajan.
Thanks, Nitin. Shravanti, can you introduce yourself?
Yes. Hello, I'm Shravanti. I'm a PhD student in the ECE department at IISc. I did my BTech from IIT Tirupati. I graduated my BTech in 2019 and joined here in Professor Sandeep Prabhakar Chepuri's lab in the same year, 2019. My area of research is machine learning with graphs.
Thanks, Shravanti. Maybe what we'll do today is like, I'm not sure how many of you have been attending the previous lectures. So the idea of this discussion is just to make you guys aware of the nature of the interview, the kind of questions to expect, and what the interview panel expect from you guys. So this will not be something that is very technical. Like, I mean, we do solve few questions, but we won't be focusing more on the equations or things like that. But it will be more like what exactly is the expectation from you for a given question like that. And it will be really great if we could make this a bit interactive, because that's kind of nice for both of us. Uh, and yeah, so if something is not clear, or if my audio is getting disconnected, or like if I'm going too fast, please feel free to interrupt and let me know. And yeah, so if any of you have any doubt at any given point of time, like please raise your hand. One of us will take your question. So I think we can start with this. So transform theory is one of the topics that is very important, especially for people who are applying for signal processing and communication. So this basically deals with the subjects of a Fourier transform, Laplace transform, and C transform or set transform. So, and unlike the topic where we have like linear algebra, where questions are from linear algebra itself, in transform theory we can also have questions the where we are more interested in the application of these transforms rather than the transform themselves. Like they may not ask how define a Fourier transform, but they might ask about like more things like how can you apply these transforms in the study of signals and systems in general. Especially there can be questions on sampling theory, LTI systems, filters, and so on. So this is not an exhaustive list. This is just a brief overview of the topics that are generally asked in this area. And the kind of questions that we will discuss today are basically the questions that we have been asked when we were given the interview like for 3 to 4 years back. So again, like if something is not clear, please let me know. So the plan is that I'll begin by explaining a few things about sampling theory, and then Sravanti will explain about LTE systems, and then Nitin will explain few more questions about filtering and associated topics. So that's the plan for today. And once again, please do interact. And yeah, maybe before beginning, is anyone having any doubt or any clarification about this session? Like, please unmute and ask, or you can raise your hand. Either way is fine. Do you have any questions? Shall I start?
Yeah, there are no raised hands. We can
Okay,
start.
okay. Sure. Okay, thanks. Okay, so I'll begin by explaining sampling theory. So I want to make it a bit interactive. So can any one of you tell me what is sampling? So what do you mean by sampling a signal? Can any one of you please unmute and tell that? Hi guys. I don't think it's working the way I expected it to work. So
It may sound a little vague, but I think given a signal to split it up as per time or frequency, to split it up into intervals, so that
okay.
In one of the dimensions, it may not be the exact definition, but
Yeah, so what you told is correct only. So can you explain in the sense of our usual time domain? Like let's say if you have one dimensional signal like time domain, then maybe I can draw a graph like I have signal x of t here, something like this. So basically when I say I'm sampling this signal, what it corresponds to?
you can sample it with respect to time and say in a duration between 0 to t1, say, you can have n samples. You can split it up into n parts.
Correct. So what you're saying is that we basically convert this continuous signal and we won't take all the values of signal. So right now this is a continuous signal. We discretize it. Correct.
Yeah.
Exactly. So what we do is we have this continuous time signal. Now instead of taking all the values here, we restrict ourselves and look at only the values at certain time instances. That's the idea of sampling. I think all of you are clear with this. And Karthik, what is this A to D? Can you explain, please?
I meant discrete.
Yes.
It's a discrete stuff after sampling the final product. The discrete stuff.
I see. Nice. Actually, a better way to answer this question, in my opinion, is that we can tell that we are discretizing the time index. Because if you say analog to digital, that could also mean that we are discretizing the y-axis. That could also be a case, right? So,
okay.
So generally, when we say sampling, we mean this kind of discretization. We are discretizing the time axis as far as the our usual time domain signal x of t is considered. Now, there is also another thing, like let us say if you have the signal and you don't want all the values in y-axis, you want only certain values in y-axis. That also you can do, right? That thing is known as quantization. This thing is known as quantization.
Yes.
Yeah. And whether the screen is shared, can't you see the screen?
It's clear on my side.
Yeah.
Yes, sir, we can see.
Actually, I can't see the screen.
Okay.
You can't.
Can you just do it again?
My name is Nivedhan. Whether I should rejoin the meeting?
Can you try that once? Like if it's still not working, maybe I'll just reshare again. But can you just rejoin once and see? Yeah, I think others find it okay. Yeah, it's visible fine. Okay, so so we just seen what is sampling. Now, my next question is like, okay, so sampling, once you take the samples at these time intervals, we have, let's say gap is t. And from this, let us call these values as the sampled values to be like x of n. That's the usual notation that we use. Now, did he join back? I'm not sure. I think he just left. Okay, I think, yeah, maybe I'll continue. So, okay, now that we know what is sampling, my next question is like, what is, I can see Karen, bro. Okay, fine, yeah. So, now that we define what is sampling, can anyone explain what is this Nyquist sampling theorem?
Fs equals to 2fm, like double the message frequency.
Yeah, your answer is completely correct, but there is a slight problem with this. So this is exactly the reason I asked this question. So many times we only tell the formula, right? So in interviews, like when they ask to define something, like it's better that we tell it in words. So your answer is completely correct. I completely agree with that. So who answered actually? Maybe can you unmute?
Yes, sir.
Okay, yeah, nice. So let me. So you told that fs more than equal to
2 FM, sir.
2 fm, right?
Yes,
Can you
yes.
tell me what are these things? Fs, fm, and all?
FM is the message frequency, highest bandwidth frequency,
Okay.
and FS is the sampling rate of frequency which we have done for the sampling.
Okay. Okay. Suppose that I do this. Suppose I choose fs more than equal to 2 fm. Then what? Like, what is the advantage of doing that?
The aliasing does not occur in the system.
That is also fine. Suppose I don't know what is aliasing. So what is the problem with aliasing?
Aliasing means the way when we multiplex some message signal, the message signal will overlap to each other.
What's the
Then
problem?
the overlapping to each other, the message signal.
Okay, so suppose it overlap, then what's the problem?
The message disrupted or message can be the message are overlapping, so the amplitude are double and summation are there.
Correct, you're right, you're right. Yeah, so you're completely correct. But yeah, so so from my suggestion is like what they generally ask from. So your answer is correct. I mean, it's correct only, but we can make it even better. So generally, when the panel is asking this question on sampling theorem, not just this question, in any question, so they always want to see the concept behind that. So in your case, like when you initiate, I mean, I'm not telling this to, I mean, I'm not picking you or something like that. I don't think of it like this. I'm just giving a general suggestion. So the first answer that, and mostly everybody tells is that when asked what is sampling theorem, they say fs more than equal to 2f. But that is correct, but incomplete. Why is it incomplete? Because it doesn't tell what are we doing. It doesn't tell what happens when this is satisfied and things like that. And when I asked, you are correctly answered that aliasing will occur. But even that is incomplete. Like why aliasing occurs or why even aliasing is important. That's another question that they will ask. So the way that they generally expect the solution is like this. So the story goes like this. Suppose we have a continuous time signal x of t. This is having bandwidth b or fm, doesn't matter. So suppose I have a continuous signal x of t having bandwidth b. Now what the sampling theorem says is that I take the samples of this thing at fs more than equal to 2b. I get x of n. Suppose I do this. Now what happens if I do this? The sampling theorem says that if I sample a continuous time signal x of t having bandwidth b at a rate at least more than twice the bandwidth, then I can perfectly reconstruct the signal back from the sample x of n. That's the key point here. So why are we worried about this sampling theorem? The reason is that if you choose your rate like this, then given this x of n, I can go back to x of t. I can reconstruct the continuous signal from the samples itself if I satisfy this property. That is the complete idea of sampling theorem. And now question can happen, how do you do this reconstruction? So the answer is that you can do this through what is known as sinc interpolation. So any questions on this? It's good to have more discussion. I think that's better.
Sir, can you elaborate the sinc interpolation?
Exactly.
Actually, I don't know that term.
Yes. Yeah. So what happens here is I'm so to explain what is sinc interpolation, what I can do is I can show the proof of sampling theorem that I'm very sure all of you might be already familiar with, like that picture where this overlap happens. That everybody is familiar, right? Maybe I think you can bring. Yeah.
Yes, sir.
Yeah. So how do we prove the sampling theorem? By the way, if anything is not clear at any time, please let me know. So how do we prove the sampling theorem? We consider a signal in the Fourier domain, right? We do the proof in the frequency domain, correct, right?
Yes, sir.
I have something like this. Some shape doesn't matter, but I have some shape like this where the endpoints are b. I have minus b to b. This is my signal having bandwidth b, correct, no?
Yes, sir.
Okay. So what when we do the sampling, what happens? So I'm going to write the sampling operation something like this. So when you have x of t, you multiply that with the delta t minus nts, then you'll be essentially getting an impulse. If you do this business, you'll be essentially getting an impulse at the location nts with the strength corresponding to x of nts. This is what happens when you sample, right? When you multiply your time domain signal with the impulse at that position, you'll get something like this. Correct, no?
Yes, sir.
Okay. Now, what can we do? So we can see this thing in the frequency domain. How it will happen? I have my let me open a new page here. I have my actual signal, something like this. Shape doesn't matter. I have something like this. This is my x of t. And I'm multiplying this with a series of impulses. That is how we do sampling, right? We have this impulse train. This is called an impulse train. Have something like this. Many impulses, each having separation t. Let us call delta t, this one, and this is x of t. So when you do sampling, what you're doing is you're basically multiplying this signal with this signal. Does everybody agree with this?
Yes,
Correct.
sir.
Correct. No. So what happens in the frequency domain is if you do multiplication in time domain like this, in the frequency domain, that will be convolution. That also you guys are familiar, right? Correct. No. So if you do
Yes, sir.
time,
Yes.
yeah. So you have your signal something like this. It goes from minus b to b. This is your omega or f, doesn't matter. Let me write this. Doesn't matter. Frequency or angular frequency doesn't matter. So once you see the so you do this in the frequency domain. In the frequency domain, impulse is again an impulse. That also you guys remember, right, from the derivation. Somewhere you might have seen. It's not very important, but yeah, if you multiply, this is time, this is frequency. When you have a time domain signal x of t, something, it's not a sine wave. I'm just drawing some random shape. Let's suppose a corresponding spectrum is like this. Now, if you multiply with an impulse train like this, it is same as convoluting with an impulse train like this, something like this. The key thing here is that the spacing is fs. That's the main thing. This is also, I think, you're aware of, right?
Yes, sir.
Yeah. So when you do convolution of anything with an impulse, what happens is this same shape, whatever we have, this shape will come and sit on top of each of these points here. That is how we get the sample spectrum. Correct, right?
Yeah.
Yeah. So what we have something like this. We have minus b. Then we have something at center fs, like fs minus b, fs. Yeah. This is the point fs. So I have fs minus b, fs plus b. And it will be there, like infinitely many of them will be there. Like there. We have minus fs here, minus fs plus b, minus fs minus b. Up to here is clear, no? This is how the spectrum looks like once you sample, correct, right?
Yes, sir.
Yeah. Now, what we are saying is that suppose I multiply this thing and only take this part, like this part I have here, like let us call this as some minus fs by 2 and this is fs by 2. Suppose I multiply this sampled spectrum with a box function that we have here. This is known as low pass filtering. That correct? No, this is. If I do that, what will I get? I'll get the same thing back, right? I'll get the same shape back, minus BB. I have the same spectrum back, correct, right? You agree?
Yes, sir.
Yeah. So what the sampling theory says is that if you choose this fs such that this point that we have here is not coming within this, like if these 2 points are non-overlapping, or what it means is that if fs minus b is to the right of this point b, then we can actually ensure that if you multiply this actual signal with a box like this, you'll get back the actual signal. That's the idea. So if you multiply this sample signal in the frequency domain with a box, you will be recovering the original spectrum. Correct, no?
Yes, sir.
That's the idea of sampling theory. So what it tells you is that this sampling theorem essentially gives a condition that it tells that if you sample the signal at a given rate, that is fs more than 2b, then you can perfectly get back the original signal from the sample itself. That's the result. Now, coming to your question, why do we have the term sync interpolation? So this is also something that is there. So here I have drawn this function, right? I have some filter like this. I'm multiplying my sample thing with a box function, correct, no?
Yes, sir.
So this is in the Fourier domain. If you see the time domain signal of this rectangular box function, you will be essentially getting what is known as a sinc function.
Yes, sir.
You recollect that, right?
Yes, yes, sir.
This is the reason. So if you do multiplication with this box function, that will amount to doing a corresponding convolution with a sinc function in the time domain. I'm not writing the equation here, but that you can understand, right?
Yes, sir. Yes.
That is the reason this is not a sinc interpolation. Like the process from which we go from xn back to xt. That is called sinc interpolation because we are doing this operation. Is that okay?
Okay, sir. But does it familiar to the inter-symbol interference? The both are same thing.
Inter-symbol interference, actually, no. This is related to inter-symbol interference. So in this case, even though we draw multiple shapes like this, each shape is a copy of the same thing, right? We have only one signal here.
Yes, sir.
So what happens is the right word here is like if you have one, let's suppose that I'm having I choose some wrong frequency, I have something like this or something like this. So for this much duration, there is overlap.
Yes, sir.
This overlap, this overlap is known as aliasing, not inter-symbol interference, aliasing.
Okay, sir.
Suppose I'll come to a thing. Suppose I have two different. So this is very much similar to the inter-symbol interference that we have in digital communication. There we are looking at two different symbols and a two different time instance. So there, if overlap occurs, then we say ISI. But here we call it as aliasing. This overlap is known as aliasing. Correct, right?
Oh, okay, sir. Okay.
Okay, clear, no?
Yes, sir.
Yeah. So the moral of the story is that what is sampling theorem? Sampling theorem essentially gives a condition where we can perfectly get back the actual signal from the samples. And what is the condition? Condition is that you should choose the sampling rate to be more than twice the bandwidth. That's the idea. And how do you get back from this thing to this thing? You had to do sinc interpolation. So all good?
Yes, sir.
Okay. Thanks. Now, I think, my part is mostly this. So before handing it over to Sravanti, let me give some brief tips here. So the main thing that the faculties are looking at is this connection. Like you have this continuous time signal, you have this discrete time signal. What is the condition that you need to ensure from going from here to here so that you get back a perfect reconciliation? Now, there are few things which I deliberately missed in this explanation. First thing is that I just drew any random shape here, right? So the thing is that it doesn't matter. Only thing matters is the bandwidth is big. It doesn't matter what shape you have. It could be like some rectangle, anything in between. Doesn't matter. So outside minus dB, it is 0. Within that range, it could be anything. That's the idea of a band limiter signal. Following?
Yes, sir.
Yeah. Now, other thing I skipped here is I did not tell what is the value on the y-axis. If you see textbooks, they will usually use some A or something like this here, the amplitude in the frequency domain. I did not mention that. The reason is that is not very important. Amplitudes you can adjust by scaling it later. So that's not very important. If you really want to make it very concrete, if you have something like, let us say, if this is amplitude A, and if this is amplitude, if this amplitude is 1 here, it will be 1 by T here, if you really do it correctly. So then once you do the sample spectrum, each of this thing will be having amplitude A by T. If you see in textbook, that will be how it is. Correct. You recollect somewhere, right? I mean, you might have seen this 1 by T business somewhere.
Yes, sir. Yes, sir.
So then once you do this box filtering, you need to write this box itself as gain T so that the T and T get cancelled out. That's generally how it's done in textbook. Correct, no?
Yes.
Yeah. So my thing is that it is okay to forget this T part. I mean, that's not very important. Like this amplitudes are not very important. The concept lies here. Like if it is overlapping, that's a problem. If it is not overlapping, that is not a problem. That's the main concept. So it is very rare that they will ask you to mention the amplitude directly. They can ask, but more importantly, you should be aware of what is happening on the x-axis. That is very important. That is what controls how can whether can you really reconsider this thing or things like that. Scaling is okay. It's not a big deal. So even if you forget at that time, it's not a big problem. This T thing, they don't worry much about that. But this B, Fs minus P, these locations should be correct. That's the moral. Is that okay?
Yes, sir.
Okay, so yeah, you told the correct answer, but this is a way to improve it even further. And one general advice, like the way this interaction works, the best is like we can ask a question and we can interact. So if any one of us tell that the question is incorrect, it's not to demotivate you, it's just to improve your presentation further. We are just when I was given the interview like 4 years back, I also did not tell all these things. Like I might have probably answered that Fs more than 2b itself as a sampling theorem, but yeah, this is just we are telling our experience to you guys. So don't think that we are like picking on somebody or that's okay, right? So yeah. So so far any doubts? So any question here?
So there will be a factor of T, right? Which is an amplitude of that low pass filter, I think.
Correct.
That is what you're trying to say.
Yeah. There will be a factor of T. So the thing is that it's always good to write that, but even if you miss that part, it's not a very big problem. But if you miss these indices wrong, then that's a problem. Because that, I mean, these locations are very important. That controls the theorem.
The impulse of 1/t is what makes it a by t, right?
Correct. No, the impulse is actually one only in time domain. Once you go to the if you write the expression for the impulse train with unit amplitude in time domain, you do the Fourier, you get something like this. Some 1/t summation over n delta some t minus nt, something like this will come. So again, that scaling is not something that we need to worry much about, but this positions are very important. So if you have a gap of t here, it will be fs here, where fs is defined as 1/t. These are important. Fs is defined like the sampling period is 1 upon sampling frequency, like that. So even if you miss this a part, it's still okay, but shape and where it comes, that these things should be important. And more importantly, this connection should be there. Like this connection is the main reason why we have theorem itself. Okay. And so any doubt, anyone?
Can you tell me what was your interview question?
Once again.
Can you tell? I joined a little bit late. So
Yeah,
can you tell me what was the interview question that?
Question was like this. Yeah, I'm audible, right?
Yes. Yes.
Okay. Okay. So the question was like this: define sampling theorem.
Okay.
So most of the time, like maybe you want to take a shot. Like, can you define sampling theorem?
Yeah. Means if someone asks me, I'll just say that the sampling rate should be more than the twice of the highest frequency present in the signal.
Okay, so your answer is correct, but there's a slight problem in that. Suppose you tell that, so they will ask why. Why do you want that to happen?
Because in that case we don't lose any frequency. Means means if the sampling frequency is less than the twice of the maximum frequency, then we may lose some information. Yeah.
But why?
So
that is also correct, but where is this information coming from? Like where exactly do you see the loss in information?
That overlapping is coming. That is what that we have shown.
Okay. So what's the problem? Like suppose there is an overlap. What is the problem?
Well, we won't be sure if that the information is coming from the signal which is centered at 0. Correct. Or the signal which is centered at fs.
So even that is okay, but suppose I have something like this, or even suppose there is no overlap, then what? Like, how can you say that no information is lost if there is no overlap? Can you?
If there is no overlap, then I don't think there will be any information loss because frequencies are not means the frequency of means one image is not interfering with the means frequency of one triangle is not interfering with the frequency of the second triangle. So I don't think there will be any information loss.
So there won't be information loss, but the key thing that is again missing is like how do you define this information? Like suppose I ask you, can you give me my actual signal from this sample signal? Can you do that? That's the question. So given this xn, can you go back to xt? So that is the main thing regarding sampling theorem. Whatever you answered is completely correct. Only thing is that the information that you're referring to essentially amounts to the reconstruction of this continuous time signal from the samples. Correct, right?
Okay.
So the So the main thing here is that when we want to define sampling theorem, the idea is that we have section given the sample x of n, how can I go back to the continuous time signal x of t without any loss in information? So that is so the information is coming into picture because I want to go from here to here. That's the reason. Following, right?
Yes.
Yeah. So a better way of answering the sampling theorem is like this. So suppose I have a continuous time signal x of t with bandwidth b. Now, if I sample this at a rate more than twice the bandwidth, then I can go back from xn to xt perfectly without having any error. That's the idea of sampling theorem. And how do I go back from here to here? I use what is known as sinc interpolation, or I'm multiplying this with a low pass filter in the frequency domain. That's the idea. You follow, right? If I just do something like this, and if there is no overlap, I'll get back what is needed. Correct, right?
Yes.
Yeah. So that's the idea. And yeah, so all good. Like, shall we proceed?
I think there was a raised hand.
Sure. Yeah. Who raised hand?
Okay.
Narayan Mishra?
Yes, sir.
Yeah.
Sir, yes, sir. I have a question. Sir, in interview, they ask the basic questions like you told us. Sir, we answer them. But then they create a
Can
very
you
tricky
say once again? Actually, your voice was a bit broken from my end. I think it's my internet, but yeah.
Sir, it is now clear?
Now it's clear. Please.
Yes, sir. Sir, in the beginning, they just ask a very simple question like define sampling, as you told us. Sir, I know the basics. I tell them, and then they create a tricky questions from there. Like, sir, in this question, they will ask us, what if the message signal is bent pass? What if the shape of message signal is something else? At this type. So, sir, what should be the thought process to approach such type of questions?
Very
good question. Yes, sir. Sir, as in my previous interviews, they asked some questions. Sir, in the interview, I was not able to process it. Sir, in IISc itself, in communications, MTech ECE department, sir, they ask a question. I was at that time, I was not getting what they are means, what they want the answer from us. I was answering from all the aspects, all round, but I was not able to get to the point what he is trying to ask. So, sir, what should be the thought process in the interview itself? And sir, as I came out of the interview, in just 1 or 2 minutes, it clicked in my mind, and I think that I have to answer like this. Sir, how to solve this?
That's a very good question. Thank you for asking. Actually, this is a common problem with everyone, including myself, when I was attending the interview. So let me break it down to different parts. So first question is like you told, they will start from the basics. So they ask from what you know and things like that. Now, suppose they ask a bit more tougher question. So what you should ideally think is like, if so you think based on what you answer already. So if you answer this question in the way I explained, like suppose I have a signal and I do this sampling in time domain fs more than 2b, then as long as there is no overlap, I can multiply with a box function and get the original thing back. That's a key point here. The key point is not that this, the key point is that I can get the actual signal back if this is true. You agree, right?
Yes, sir.
Yeah. So now they could ask many different questions. Like I'm giving a question like this, I'm not asking in a very formal sense, but just to give a quick idea. So suppose, so these kind of signals that goes from -b to, I think I'm taking too much time, but I think this is useful. So I have a signal like this, like x of -bb. This is called a low pass signal or a general signal. Yeah. Now I can also have a different case. I can have a signal that is something like this. This is -b. This is b. But let's say this is b by 2. And this is like some b by 4. It could be, I mean, I drew it pretty bad, but yeah. So this case, this is a different signal. So what's the main difference between the signal that we have here and here? This is known as a low pass signal, and this is known as a band pass signal. I think this is what they might have asked you. So here, the key difference is that in this case, you have information continuously from, I mean, everywhere from -b to b, whereas even though you have up to b by 2, the actual part is only b by 4 to b by 2. It's not entire range, correct, no?
Yes, sir.
Yeah. So if you want to sample this signal, you don't have to do fs more than equal to 2b because there are so many empty spaces in between. If you can get a spectrum where there is no overlap, like let me draw it like this. So I have from this is b by 2 4. This is b by 2. This is again minus b by 2 minus b by 8. So in this case, if you can get a spectrum, so information is only here, right? I mean, I only need this shape back. I don't need the entire thing. If I have that shape, I can get my actual signal. That's the idea, right? So
Yes, sir.
once I multiply this thing with the box function, I just need to recover whatever it was earlier there. That's it. Now for these kind of signals, this and this, they're same. You agree?
Yes, sir.
It will be always like that because if you have a real signal and you do the Fourier transform, it will be always symmetric like this. You agree, right? Now, if you want to reconstruct this one, any sampling rate that ensure you have at least one piece like this, that will be sufficient. So you need not do fs more than equal to 2b. You can actually do at a much lesser rate. Now, they might not expect you to come with an exact expression because that's actually a difficult question. I agree. But the thought process is that, or the thing that we need to convey is that the main reason why the entire sampling theorem exists is like, how can you choose the frequency so that I can multiply with a box and get the original shape back? That's the main thing that we need to focus on here. You agree?
Yes, sir.
So the solution to this question, I'm not directly writing the final answer here, but maybe you can think about this. This is known as bandpass sampling theorem.
Is the answer f is greater than or equal to b?
In this case, you can actually do, let me, so effective bandwidth in this case is b by 2 minus b by 4, which is b by 4. So I think fs more than b by 2 itself will be sufficient, I think, because the bandwidth is only b, right? It's not b by 2, like it's the same information on both sides. Correct, no?
Yes, sir. Sir, my question is, sir, I know bandpass sampling. What is bandpass sampling? I just create a situation that they create some questions. So how to approach those type of questions in the exam interview? How to think for that ones?
So yeah, my suggestion is that I think if you think along the lines of the theorem itself, like if you, instead of thinking that fs more than equal to 2b is the sampling theorem, what I actually want is like, if I have a spectrum like this, as long as I can find the same shape in here without any overlap from adjacent things, I can always multiply that with a box function, appropriate box function, to get the actual signal back. Correct, no?
Yes, sir.
So even if you tell this much, they will be convinced to an extent. Then they will ask further questions. So they mainly expect to answer this part. This is the most crucial part in sampling theorem. Like you should tell what you are doing here. So fs more than 2b, that's not the main thing. Main thing is I should get something where there should not be any overlap. And why is that important? Because if there is no overlap, I can always multiply by a box, something like this, and get back the actual signal. That is what they're looking for. Even if you answer up to that, they will be convinced. Yeah, so in general suggestion, like don't go behind formula, like any formula, like fs more than 2fm, or like there could be many other formulas in the subsequent discussion. They just want the concept. Concept in the sense that concept is not that I do fs more than 2b. Concept is that I have a shape here. I can sample in whatever way I want, as long as I ensure that I have a piece intact here. If that is the case, then I can get it back, right? That's the idea. Okay.
I have two questions here.
One second. It's a previous question. Are you okay with that?
Yes.
Narayan? Okay.
Yes, sir. Yes, sir. I understand.
Okay. Thanks. Yeah, Priya, please.
This 1 by t is the magnitude of this particular impulse that you're showing here, right? Above the, that is what it is, I think. Just checking. Correct. It's not minus, there's no minus sign, right? There
is minus?
No, there's okay, that must be something with the representation. 1 over t only it is.
Yeah, 1 over t. There is no minus, no.
And the second question is, what is the relation between FM and bandwidth?
Nice. That's a good question. So there are different definitions of bandwidth. So suppose you have a regular band pass signal, low pass signal, something that looks like this, where the spectrum is continuously occupied from not continuously, but it's there from minus b to b, something like this. So in this case, this is the bandwidth. Correct, no? This much will be the bandwidth. You agree?
It's not twice of that.
No. This bandwidth means like okay, I can give a general definition. Bandwidth, like the name suggests, that is the difference between the largest frequency and the smallest frequency.
Okay.
So when you write something like this, so even though the width of the shape looks like 2b, the bandwidth is like b. So some textbook and some people actually use 2b for this, but then if that is the case, then you should follow that continuously. So generally, when we say bandwidth, we always define bandwidth as the difference between largest frequency and the smallest frequency. Correct, right? Bandwidth, the width of the band. So in this case, this is the largest frequency, this is smallest frequency. So in this case, bandwidth is b. No, I can have another
You're
case.
taking absolute values, I think.
Largest minus smallest will be always positive, right?
Yeah. Can I?
Yeah, yes,
so
please.
see, yeah, right. When you think about, don't think in terms of just looking at the graphs. See, this frequency response, what you get is a mix of multiple equations and all those. But what it means is that at 0, it means DC. You can't go negative in frequency. Okay, so this is just part of the representation. But in reality, in practice, the frequency starts from 0 and goes up. So from that point of view, bandwidth starts from 0 and goes till B only. So it's the bandwidth, if you look in a practical kind of scenario, is B, not 2B. Does that help?
Thanks, yeah, that's very important. The frequency, like as we know, is always something positive. So spectrum we are drawing minus b to b, but the bandwidth, like you told, it's about the minimum frequency to maximum frequency. Like if you have something like this, then bandwidth will be fh minus fl. It won't be 2fh, and it won't be fh. It's fh minus fl.
Ashok, also draw the negative part, then it will be more clear.
Oh yeah, sure.
If I can add one point.
Yeah, please.
These negative frequencies, I guess it's they help in the completion of this mathematics. That is, this cost becomes e power j omega t plus e power minus j omega t divided by 2. I think it is this negative frequencies are drawn only for the sake of mathematical completion, and there is no physical significance.
Exactly, you're right. Completely right. That just comes from the max, like once you do the transformation. You're right. Thanks. And Priya, is that fine?
Yes, that is okay.
Okay. So
but I think you have to get to that point between FM and bandwidth, right?
What is FM? FM is, sorry, FM is FH for me. Maximum frequency you mean, right? FM.
Okay.
Yeah. F max or FM something.
So okay. FM is equal to bandwidth. Fine. I think that is okay.
No, I didn't tell FM equal to bandwidth. I told bandwidth is the difference between these two things. So for this one is FH minus FL. Okay. This is not 2 times. No 2 there. 2 is not there. Just FH minus FL.
Okay.
And
in the first case that you wrote, it will be 2B is equal to 2FM. That's what it is. That's what you're trying to say. In the very first slide or the second slide that you wrote. Right there. Fs greater than 2FM, and the same condition is Fs
equal to 2B here in this case.
Which is the same as Fs greater than or equal to 2 times Fm.
Yeah, you're right. My general suggestion, like I don't know. I mean, if I might be wrong here, but like the main thing is not the formula. Like it's not about the formula. FM, FH, I can call it by different names, right?
Yeah.
So the main thing is that
it is the bandwidth is nothing but the difference between the highest and the lowest. That's all it is.
Exactly. So if you want to give the safest answer for sampling theorem, you can give it like this. Sampling, I mean, given that you the other stories also there, like this, the condition that you can perfectly get back is sampling frequency more than equal to twice the bandwidth. That's it. Now we can have different names for sampling frequency. Generally, we use FS here and we use B or FM or anything. So generally, it's good to say in the theory sense, like sampling frequency more than twice the bandwidth. Now, what is bandwidth? Bandwidth is the difference between highest and lowest frequency. And in general, we always do things like this. But if you have special cases like some band pass, somebody else is unmuted or like. I'm getting echoes back actually. Priya, I think may not be from your end. I think I don't know. Maybe let's see. So yeah. So unless we have some special case like this is good. Now I'll give one more suggestion. Like this is like a what do you call like the final ditch thing. Like if you're completely confused at that time and you're not sure what to do, you can always sample it twice this thing. Let's say if you have something like this, even if you have something like this, like if you have this is FH, this is FL minus FH minus FL. You can also reconstruct, you can exceed the rate, right? I'm only telling greater than or equal to. So the worst case scenario, if you are not able to correlate, I mean, in general, if somebody is not able to correlate at that, at least you should tell that FS more than equal to 2FH. At least that is not the sampling theorem in general, but if you do this, then definitely it can be done. Okay. So if you can sample at a rate more than twice the highest frequency, that is always guaranteed you can come back. But sampling theorem says that it's sufficient to have twice the bandwidth. That's it. Is that okay?
Yes, yes.
But generally don't, it's not good to directly draw a shape like this. Like my general suggestion, if anybody asks for sampling theorem, draw this one. That is easier for us to explain. Start with this and explain with that. Don't go with this thing. That will give more questions. Anyway, they will ask more questions, but yeah. Is that okay? Okay, right. Thanks. Any other question? If maybe Shravati, you can already share the screen, I think.
Hello?
Yeah, Deepankar, yeah, please.
Yeah, all these graphs, they are the amplitude frequency spectrum, right? Amplitude spectrum, right? So, so my question is that why in each every time we see that there is a symmetry, means the graph is symmetric on the positive side and the negative side. So, why is it so happening every time?
So the symmetry is a consequence of the fact that it's a real signal. So there's a theory, there's a result that says that if you do the Fourier transform of a real signal, I mean real valued signal, then the spectra will be always symmetric. That's a result. That's a consequence of the math.
Okay.
But if you take the Fourier transform of a complex signal, you won't get it symmetric. That's also there.
Okay.
But generally signals are real. So yeah. For real signals, spectra will be symmetric. Okay, no? To be more precise, if you have a real signal, your magnitude spectrum will be even symmetric and your phase spectrum will be odd symmetric. That's the more precise answer. Is that okay, Deepankar?
Yes.
Okay. Shravati, you can see your screen. Okay, maybe I think.
And I'm also audible, right?
Yes, you're audible. Yeah.
Yes.
All good. Maybe I think yeah, I'll keep muted. You can take you can explain and yeah, okay, thanks.
Yeah. So okay, so now I'll discuss a few things about linear time invariant systems. So in the interview, your questions could start from as basic a question as what is a linear time invariant system? So would anyone try answering that? What is an LTI system?
Yes, ma'am.
Yes, what is it?
Ma'am, in LTI system, whenever an input is a continuous time input is applied, and so, ma'am, basically defining the system LTI, linear time invariant. Sir, it has three properties: linear and time invariant. When a system response, we have a system impulse response. When the impulse response satisfies the properties, linearity. Linearity means homogeneity and superposition both simultaneously. And the property of time invariance. Then that system we can call it as a linear time invariant system, LTI system.
Perfect, right. So when you're asked what an LTI system is, you will basically say it is a system that is both linear and time invariant, right? So the
Yes, ma'am.
next obvious question would be, what is linearity and what is time invariance? Correct. So what is linearity?
Ma'am, as I said, a signal which satisfies both homogeneity and superposition. Ma'am, homogeneity
Yes,
implies, yes, ma'am.
Yes. This has
Yes, if
two parts to it. It satisfies both additivity and homogeneity. We call it a linear system, right?
yes, ma'am. Yes, ma'am.
Now, what is additivity and what is homogeneity? Let's
Ma'am,
take a system. Yes, let me just finish drawing this. You have an input to the system and an output y of t. We represent the system by some variable say t, right? Now, instead of x1, let me say, when the input to the system is x1 of t, the output of the system is y1 of t. And when the input is x2 of t, the output is, say, y2 of t. Now, what is additivity? When do you say a system is additive? When you give this
x1 has x2t will give y1 has y2t.
right. When you give the sum of these two inputs, x1 and x2, as the input to the system t, the output will be the sum of the outputs when the inputs are x1 and x2, right? So this is additivity. And what is homogeneity?
If we multiply the input by a scalar, then the output will be multiplied with the same scalar.
Right. This is what it is, right? So this is homogeneity. And now that we've answered what linearity is, there could be questions about examples of linearity. You could be asked to give a few examples of linear systems. Would someone do that? Some examples of linear systems, like a very simple example could be y of t is 2 times x of t, right? Any more examples of linear systems?
Can we
Is
just
this
say
linear?
that?
Yes.
Yeah, can we just say that there are no new frequencies in the output, and then that is this, it is linear, because non-linear usually produces new frequencies.
I'm sorry, what was it?
Usually any non-linear system produces new frequencies. Here, any system that does not produce any new frequencies apart from the input frequencies, can we say they are linear?
Prashov, maybe could you help?
Yeah. So what you answered is like kind of correct. So so it's actually the other way around. So suppose that you have a linear system, then in a linear system you will not get any new frequency components at the output. But yeah, I mean, if you can say that I have a system where whatever may be the input, I'll always get an output having no new frequency components, then that's a linear system. Yeah. Who asked Karthika?
Yes. Thank you.
Is that okay?
Yeah. Thank you.
Yeah. Thanks.
Okay, coming back to examples. More examples of linear systems. Is this linear? Is differentiator operator linear?
yes, ma'am.
Yes, it is.
Yes.
Is this linear?
Yes.
Okay. So we all know what linear systems are. Now, so we were defining what an LTI system is. So like we said, it has two parts, linearity and time invariance. And we also defined what linearity is. Now, what is time invariance? Let's consider the same example. And yeah, here this should hold for all inputs x1 and x2, right? Similarly, this should hold for all scalars alpha and all inputs x of t, or rather x1 of t, right? And yeah, now time invariance. What is time invariance? If this x1 is the input to a system, y1, and we know that the output of the system is y1 of t, we say a system is time invariant if time shifted input is given as input to the system, the output would be shifted by the same amount, right? Now, if you're asked examples for time invariant systems, what would they be? Some examples of time invariant systems? Any example? Is this a time invariant?
Yes.
Yes. Is this time invariant?
Yes.
Yes, ma'am.
This?
No.
Why is it not?
The factor t will make it time.
Yeah. When x1 is the input to this, tx1t is the output, or rather when x of t minus t naught is the input, the output of the system would be t of x t minus t naught, and what is y of t minus t naught? Right? And so this is not time invariant. Now, okay, so when do you say a system is linear time invariant? When the system is both linear and time invariant. So which of these things are LTI systems? Is this LTI? Yes, it is, because it is linear and it is also time invariant, right? Is this LTI?
Yes.
Is this LTI?
No.
Because this is not time invariant.
Linear time invariant system.
Yes. And is this LTI?
No.
No, because this is not linear, right? And this?
No.
No. Okay. Then okay. Maybe one final example. Is this LTI? Is this linear?
Linear but non
Yes, this is-
invariant.
You say it is not time invariant?
Not time invariant.
Why do you
It
say
is
so?
an LTI system.
Sorry?
Ma'am, except it is not time invariant because x. Ma'am, when we give the input x of t minus t naught, then it will be x of 2t minus t naught. 2t minus t naught. Ma'am, t minus t naught is 2 is not out of t minus t naught. It is 2t minus t naught. No bracket inside.
Yes. Now we'll conclude this with what? Okay. Yeah. Now that we've defined LTI systems completely, the next possible question could be about the output of an LTI system. So what is the output of an LTI system?
Sravanti, sorry to interrupt. I'm audible, right?
Yes.
Yeah, so the previous answer that I told, I already kept it in the chat, just that I'm telling again. So when asked to define LTI system, good to stick with the usual definition. If you directly tell frequency and all, that will make things complicated further on. And also, I kind of take back my previous statement. What we can say is that if it is an LTI system, then the output will not have any new additional components. But if you just say that the output doesn't have any new additional components or all the inputs, there could be complications there. I might have to think about that. So yeah. Thanks. Karthik, that's okay, right?
Yes, brother. Thank you.
Okay, thanks. Thanks, Shanti.
Yeah. And this again is for all T0 and for all inputs X. Okay. Okay. So the next possible question could be about the output of an LTI system. When the system is LTI, do you have any specific expression for the output of a system in terms of the system itself and the input to the system?
Convolution.
Right. Convolution of what and what?
Convolution of the XT and the impulse response of the LTI system.
Impulse response. What is impulse response?
The output when the output of the LTI system when the input is delta t.
Right. So this we denote by h of t. What is delta t?
Impulse.
Okay. What is an impulse? Okay, impulse function is a function that is zero everywhere except at the origin 0, and which when integrated from -infinity to infinity will give you 1, right? The area under this curve is 1, and it is non-zero only at the origin, right? And when you give this impulse as an input to the system, the response that you get out is the impulse response of the system. And you said that the output of the system would be what? The convolution of x of t and h of t, right? Now, how do you get this? Anyone? How do you get this?
Ma'am, integration -infinity to infinity x of tau h of t minus tau d tau using the formula of convolution.
Right. So if you are in the interview, for example, if you're not able to immediately recall how you arrived at this, people in the panel, members of the panel will give you hints such as they'll ask you questions that lead you towards the answer. For example, they could ask you what the shifting property of an impulse function is, right? What is the shifting property of an impulse function? It is what you've just told me, right? Or the other way of asking is, how do you represent x of t in terms of time shifted impulses, right? How do you do it? What is it? X of t in terms of time shifted impulses. Is this right? Hello? Hello?
Yes, ma'am. Yes,
Am I
ma'am.
still audible? Yes.
Yes, please.
This is correct, right? I mean, you all know this, right?
Yes, ma'am.
Okay, maybe a
I
side
think it is
question.
y of t.
Why is this right? Sorry?
No. Please carry on. Correct.
Okay. Okay, so why is this correct?
Ma'am, because delta t minus tau the means x to delta t minus 2 will be x up to itself. It will come outside, and the integration minus, yes sir. And tau inside x will be replaced by t minus 2 and
yes. Okay. I don't know if I have to show how this is true. Maybe we can consider some other variable tau prime, which is equal to, say, tau minus t. Then d tau prime is d tau, right? And what will this x of t be? No, sorry. What will x of tau times this be? This t prime. Tau is tau prime plus t. So this is tau prime plus t and delta tau prime, and this is t tau prime. And now what is, I guess there is this basic property of impulse functions, right? When you multiply x of t plus t naught with delta t, you get x of t naught, because delta t is non-zero only at 0. So this is x of t naught, correct? So this, what will you get here? You'll get x of t, which is something that is independent of the integrating variable. So this you'll pull out, and you'll have minus infinity to infinity. And this by definition is 1, right? So this is equal to x of t, right? So you know this, right? You know that x of t can be represented this way using shifted impulses as a weighted combination of shifted impulses. Now, from this, how do you go forward to proving that the output of an LTI system is the convolution of x of t and h of t? What you want is an expression for the output of x of t, right? This t of minus infinity to infinity x of tau now. Anyone, how do we simplify this now? What we know here is that this is an LTI system. So from that, how do we simplify this? Anyone?
Linearity.
Yes, you use linearity of t to what? Since this is linear, we can observe that this is like a weighted summation, right? Weighted summation of time shifted impulses. So because of linearity, you can write this as summation of t of whatever is inside. And what have we used here? We used additivity of t. Can we simplify this further? Since t is linear, it also satisfies homogeneity, right? And so what can we do? This is like some scalar alpha times a function of t. So this will be just t of delta t minus tau, right? What have we used? Homogeneity. Now from here, how do you show that the output is convolution of x of t and h of t? Anyone? Does this remind you of some expression?
Time invariance.
Yes, you use the time invariance of t. So we know that the output of the system to the delta function is h of t. So the output of a shifted version of this would be h shifted by the same amount. So what will this be? H of, correct? Now what is this? Hello. So what is the output of an LTI system?
X of t convolve with h of t.
Right. So yeah. So you'll be asked very basic questions, like the interview starts with basic questions like these. It could start with basic questions like these, where you'll be asked the definition of an LTI system, for example. And then you could be asked what the output of a system of such a system is. And you could be able to answer that. And now they'll ask you why. And you should be able to tell them why. So while you prepare itself, I guess you should think along these lines. You should think of all the possible questions that you might be asked. Keep asking yourselves why something is the answer, right? So, and in spite of that, if you're not able to recall something in the interview, panel members will always be there to help you. They'll keep giving you hints, like they'll keep asking you questions like I did. They'll keep asking you questions about what shifting properties, for example, or what are the properties of T, and so on, and they'll guide you towards the answer. Just be alert to grasp the hints, right? Okay, so should we do the...
Narayan had raised his hand. Do you
Yes,
have
sir.
any question?
Yes, sir. Sir, I have just a simple doubt. Sir, this is from a long time. Sir, in continuous time, delta t at t barabar 0, we have infinite magnitude and area equals 1.
Yes.
But in discrete time, delta n at n equals 0, we have magnitude 1 and area 1.
Yes.
So, sir, why in time domain magnitude is infinite, I know. But in discrete time, it is 1. Why is that, sir?
Sorry to interrupt, actually. Can I, Sandhi?
Yes.
Yeah, so let me rephrase and let me ask you a slightly different question. So why are you convinced that it's infinite in time domain?
Yes, sir.
Why is that so?
Sir, we represent delta t as a rectangular signal by tending tau tends to 0, rectangular t minus tau. Sir, rect of t at tau tends to 0 are using the triangular pulse. When we reduce the width tends to 0, the amplitude tends to infinity.
Right. Okay, so now the reason why we have an impulse in the time domain is like, as Shravanti explained there, like we have this delta t as input, we get the output h of t. So the main thing that connects the input x of t and the output y of t is the convolution operation. You agree, no?
Yes, sir.
So the convolution operation is something that is a continuous operation. As we see, it's an integral. Now, when you go to LSI systems like linear shift invariant systems or the discrete equivalent of this LTA systems, those are known as LSI systems. So when you come there, input is discrete, output is also discrete. You agree, right? X of n and y of n.
Yes, sir.
So there, the thing that connects the input and output is a discrete summation. There's a summation there. It's not an integration there. You agree, right?
Yes, sir. Yes, sir. Yes, sir.
So when you, so when you have an integration, we have a notion of area under the curve. Whereas when you have summation, that notion won't be there. It's just a collection of different points having different amplitudes. So that is the reason why we don't have that integration and the infinity business that we have here. There is just one. That's it. It's a single point having amplitude 1. We don't have any integration at all there. It's just a summation. Is that okay?
Okay, sir.
Okay, right? So this area of the graph that doesn't have any meaning when you have discrete signals. Like it's a collection of different points. So there is nothing. We can't say what's the area under a collection of points. That doesn't make sense. So now the answer is like why you have delta in the first place. That's also a mathematical function defined for our convenience. Similarly, when you come to the case of discrete systems, we define the function delta n for our convenience. And yeah, that's it. And to be specific, I think that's sufficient. Yeah.
Yes, sir, I got it. Thank you, sir.
Thanks. Thank you very much. Shavandi, thanks. Yeah.
Should we also do the cascade and parallel systems, or will Nitin take over?
Maybe you can just tell, I think, like we can just tell like directly, like that's a question actually asked to you in the interview, right?
Yeah.
Yeah,
Okay,
maybe you can quickly tell that. No proof, but like, yeah.
Okay. Right. So consider this system. You have one LTI system T1 and another system T2, and your final output YT is the output of T2, which takes an input given as output by the system T1, right? Now, what is the impulse response of such a system? If the impulse response of T1 is H1 of T, and this is H2 of T. What is the impulse response of such a system?
H1T convolved with H2T.
Right. How do we get that?
For proof, first we calculate x of t convolution H1T to get y1T. In second step, y1T convolve with H2T to get y of T. And third, we can convolve H1T, H2T, and then convolve x of T with H dash T to get y of T. We can compare the three equations and get to the result that H1T convolve H2T.
Is this what you said? This is what you said, right?
Yes, ma'am. Property of convolution.
How do you go from here to here? Right? Convolution is associated, right?
Yes, ma'am. Ma'am, if they told us to prove the associative property of convolution, so can you tell us the thought process?
Yes, that will be a slightly manual work, but we'll do it.
Ma'am, you can just tell us the thought process, how to approach.
Okay.
You can do so.
You will have to just expand these out. Like, for example, if you consider x1 of t convolved with x2 of t. And then this convolved with some x3 of t. So you expand the equations out. You first write the expression for this. I mean, no. We'll first keep this as it is.
Shravanti, sorry to interrupt.
Yes.
Karthik, so this question, so you are asking the proof for the associativity of convolution, right? Thought process,
Yes,
basically.
sir. Yes, sir.
So this proof
sir,
actually,
just
it's a simple proof, but it involves a bit of mathematics. Like you have like two integration and a change of variables. So you start with explaining the each of this x1 t converges to t. You have one variable. Then the next one you make call a different dummy variable, and then you kind of do a bit of massage and rearrangement to get the result. So that will actually take a bit of time. But yeah, I mean that proof is kind of straightforward. You can find in any of the standard textbook. So what we can do is if we can we take this question at the end if we have time? I think maybe in the interest of time, shall we skip this right now? Is that okay?
So we can try it by myself.
Yeah. Thank you very much. Shravani, thanks. Continue.
Okay. Another similar question could be, what if these are in parallel? What if these two LTI systems are arranged this way? And the final output of the system is the summation of these individual outputs, y1 of t and y2 of t. What will be the final output? No, not the output. What will be the impulse response of the system?
h1t plus h2t.
Yes, and how do we get that? Right, what is y1 of t? And now? And what have we used here? How did we come from here to here?
Linearity.
Distributive property.
Commutative or distributive, I am confused.
Yeah, distributive property of convolution over addition, right? And this distributivity is slightly more easier to prove, right? I guess that is very straightforward. Okay. So this is all I had.
One last question.
Yes.
Were you people asked to prove these things?
No. They'll not ask such lengthy math involved questions. They'll just see if your basics are right. I mean the conceptual part of it. This was a question that I was asked, by the way. This, I mean, the output of an LTI system and why
Sir,
this.
Actually, yes, sir. Sir, actually, in the ECE department interview, I have written the wrong formula for communication. So they just said me to correct it. So I have to go through the entire derivation over there. That's why.
Prashov, you're saying something?
Hi, thanks. Narayan, actually, that question was asked to you for the tech interview, right?
Yes, sir.
So there is the main difference between MTech interview and the PhD interview is the following. So in MTech interview, they essentially want to check how much we know. So in that case, they'll be a bit particular about the exact formula, things like that. Actually, to one of my friends, they also asked to do some pretty lengthy operations using, they want to find the Fourier transform of some complicated shape. He had to use some formulas and all. So that was for the MTech interview. Now, when it comes to PhD interview, the gender expectation is two things. Like first is like how well can you apply the existing concept to solve the question, and second is that suppose that you get stuck, then how well can you pick up the hints that they give. So for PhD, at least generally they won't ask any lengthy questions. So it will be more about concepts, like they won't ask they won't ask any lengthy proofs and all. Is that okay?
Okay, sir.
For EC department, I'm not sure about other departments. Okay, yeah.
Okay.
Thanks.
Prasad, do
Yeah.
you have any session for this calculus and differential equations?
Calculus, I think. Let me check 1 second. Josna, can you answer? Josna, I'm seeing her name here, but I'm not sure. There will be, I think, but I don't know about the exact date. So maybe you can join tomorrow's session. They will tell.
Okay. Thank you.
Is that okay, Karthik?
Yes.
So
yes,
we are not handling it.
Okay. I understand. Thank you.
Okay. Thanks. Any other doubt? Any questions? Shall we move to the next session?
All right. Yeah, I mean, I'll wait for
share,
maybe 1 or 2 minutes also. Yeah, I will share. So yeah, if you have any questions, please feel free to ask. Yeah, I'll share.
Yeah. Yes. Any of us can answer, actually. Like, feel free to ask questions.
Sir, I have a simple doubt. Sir, in the beginning, in Fourier, in the sampling, sir, when we are multiplying the xt with the delta t minus nts, and for the frequency domain, we are taking the Fourier transform of xt, and sir, we are taking the Fourier transform of delta t minus nts, or we are taking the Fourier series expansion of delta t minus nts.
So you can actually find the Fourier, you can actually compute Fourier transform even for periodic signals. Like, it's a slightly different procedure, but you can do that. So the way you can think of it is like you have an impulse train, delta ts, like a collection of shifted impulses, correct? No? Yes, so you don't have a single impulse, you have a collection of many impulses. So that kind of symbol, which is usually referred to as an impulse train, you can compute the Fourier transform. And to compute that Fourier transform, you need to use restriction Fourier series. That is needed. But once you do the computation, you will be getting an something like 1/t summation over some n delta of f minus n f, something like that. You'll get that once you do the math. Yes. But yeah, you can think of it like taking the Fourier transform of the entire sequence. And you're right, for that you need to use Fourier series to get to that Fourier transform, because it's a periodic signal. Yeah. Okay. But its overall idea is clear, right? You have x of t, you have that impulse train, do the Fourier transform of x of t, Fourier transform of impulse train, then do the dot star. I mean, sorry, then do the multiplication in the frequency domain.
Okay, sir, I got.
Sorry. I'm sorry. You do multiplication time domain, you do convolution frequency domain. Okay.
Yes, sir. Yes, sir.
Okay, right?
It's okay, sir.
Nice. Yeah. Nitin, I think, yeah, your screen is visible. Actually, I can see Teams.
Okay, I think we can move on in the interest of time. We'll get more questions from. I mean, is there any more question? No one said someone said something else. It's fine, right? Okay. I hope I'm audible. Hello.
Yes, sir, you're audible.
Yes, you're
audible.
audible.
You're audible. You're audible.
So so now Shravanti got these questions on LTI system. Someone might ask to give a practical example of an LTI system. Okay. I mean, from in a practical application or something and like that's more tangible. I'll give you one example. You can also think out of the box for different ideas. So one thing, like I'll give an example. So here, let's say a person is giving a speech in an auditorium. we hear echoes due to the reflections from the walls. Now, if the person talks louder, the echo is louder. Okay, that kind of hints at the homogeneity. And if two people talk at the same time, both echoes add up, and it's more related to the linearity property. Now, let's say if the person is at the same location and utters the same words at different time instances, the echoes sound the same, like the incoming reflections will also sound the same. And this hints towards the time invariance property. Now, this is not like a perfect system. I'm giving you an ideal scenario. Now, this is also a sort of an LTI system. System is not always a sort of something that has an impulse response. It need not be like that. System can have a different modality of input and can have a different kind of output. Okay. Now, what is a practical application of such an idea? Now, if you generate let's say if you generate the sound of an impulse, which in practical scenario, it sounds like a firecracker. If you create the sound of an impulse in the auditorium and record the echoes generated, you're basically recording the impulse response of this auditorium. Okay, this is kind of a interesting practical application. So if you record this impulse response, like you have some impulse sound and you get this echoes, if you use this impulse response and pass it through a clear recording of a speech, the final output will sound as if this person is speaking in the auditorium. And this is an interesting application of how an impulse response can be used in a practical scenario. Now, this kind of setting is used in audio, what can I say, audio processing softwares or audio processing equipments. Now, this is just an example. You can try thinking different ways, and you can even search for the internet for different examples. So, in the interview, they might ask for different examples of LTI systems or maybe some practical examples of that. So try to be aware of such, some examples in your mind that might help. And just make sure that you are explaining it through this idea of linearity, time invariance, and all those. Okay. That was just a small side thing. Now I'll get to another question, which was a little more, more involved. This is something that was asked to one of us. So the question is, what will be the output if we process a pure sinusoid with a filter having a Gaussian kernel? Now, so this is the question, and you are in the interview panel. I mean, you are in the interview. Suddenly, you are hearing all these new words like kernel, processing with a filter, and all these things. Maybe you might get a little panicky, like, oh, what is the kernel? I'm not aware of what a kernel is. Some of you might not be aware. So in such a situation, you should not be afraid that you're not aware of these terms. The panel already knows that you are not aware. You can easily ask them, what do you mean by filtering with a Gaussian kernel? You can even suggest, did you mean to say that it's a filter with an impulse response of Gaussian? They'll say yes. Or if you say that you don't know what a Gaussian kernel is, they will reply to you saying that this so-called Gaussian kernel is basically a filter, or a filter having Gaussian kernel is a filter with an impulse response being Gaussian. Okay, now it's more clearer. Wait, where is it? Okay. Okay, now you know that you need to convolve a sine wave with a Gaussian curve. Now, using the standard notations, we can say x of t is a sine wave. Let's say it's sine omega 0 t. And let's say this frequency is at omega 0. And now we have the impulse response, h of t, is equal to, can someone unmute and say what is the equation of a Gaussian signal? A basic equation. I don't need the entire, amplitude and everything.
E to the power minus 80 square type.
Yes. So yeah, that's all you need to remember. So sometimes some of you are concerned that I need to know the entire equation of that this Gaussian normal function or anything. It's not necessary. All you need is you have some scaling in this part, which which defines the spread of this Gaussian function. Okay, so you have a sinusoidal wave, you have a Gaussian wave. You are convolving it with a Gaussian function. Now, you're asked to pass it through an impulse response of Gaussian. Now, convolution, and as you know, we have some properties on transforms. Now, convolution in time domain will be what in frequency domain? Multiplication. Okay. So what will the multiplication, or maybe what will be the frequency domain of sinusoidal signal, x of omega, let's say? Can anyone try try to say, like, you can just look at the graph and say what the graph would look like of x of omega. Can someone try?
Sir, impulse is located at omega.
Impulses.
Okay. I got 3 people talking. Let's see. Ramji, yeah, you can talk.
Sir, impulse is located at omega naught and minus omega naught. 2 impulses.
Yes. So you got 2 impulses. Do you know what will be the amplitude and all those? It's not necessary that you know the exact scale, but at least it will be better if you know the phase. Yeah. So it will be some scaled version of minus j and plus j, meaning complex j. Okay. So till this point, you just need to know, I think it's some pi, there is some pi or something. It's not a necessary thing. But for now, you should be aware that it's opposite in terms of phase. I think someone's audio is coming through. Ramji, can you please mute?
Yeah, same thing. Yeah, I'm also finding some echo from here. Yeah, thanks.
Yeah. Okay. Now, so that is, see, in an interview, they're not looking for the exact amplitude or anything, but you should be aware all these things. Like it has like both of these peaks have similar amplitudes, and the phases are opposing each other for sine wave. And for cosine wave, you might be already knowing that it will be at the same phase. Okay. Now, what will be the frequency response of this Gaussian signal? Can somebody say that? Can somebody give it a try?
Gaussian pulse.
Yes. So Gaussian will give us another Gaussian in the frequency domain. Again, there are some intricate details which are not actually necessary right now. Because right now they're trying to see how well you are understanding the question. They know that if you refer to the internet, you can get the exact equations. Or if you refer to a computer program, or if you ask a computer program to simulate this so-called frequency response, a computer program can do that. So they're not looking for the exact equations. They are looking for the basic concepts. So given a Gaussian, you get a Gaussian, these kinds of concepts. Now, let's get to the convolution part. Now, if you want to apply convolution in the time domain, you need to apply multiplication in the frequency domain. So can somebody, just give it a guess, what will the output look like after applying all this multiplication and inverse Fourier transform? You can raise your hand. I think, Gunashek.
Sinusoidal with shifted phase and magnitude.
Sinusoidal?
Like sinusoidal with a different phase, shifted phase, and different magnitude.
Okay. Why do you think it has a shifted phase? So you see, consider this like I am a panelist and you are taking the interview. Now you said that it's sinusoid with a different phase. I'm asking you, like, why do you think it's a different phase?
Okay.
Feel free to answer, no problem.
That depend on the phase response of that Gaussian curve.
Like, right. So now I can right now assure you that the Gaussian curve, if it's in the real axis, even in the frequency domain also, it will be in the real part. Okay, so that's by definition like that. So
then
what will be?
Yeah, then it's just a same sinusoidal with a different magnitude.
All right, yeah, that's the correct answer. So let's say x of omega is these impulses, and you multiply that with h of omega, which is Gaussian. Now, again, at the location like omega 0 or minus omega 0, when you multiply a signal with an impulse, what do you get? You get like that same impulse at the same location with the scale multiplied to it. Okay, so that's what you get as the final thing. Now, this scale can be some arbitrary number. Now, can you say something about the scale? I mean, looking at the figure, if the frequency is higher, what will be the response? Will the amplitude go up?
It will be less, like an exponential curve.
Yeah, so depending on the Gaussian, it will go down. So what? So finally, now you got these two impulses. Now, when you convert it back, what you would get is another final output will be x of y of t will be another sine wave, which is with a different frequency. Okay. Now, from here, let's go on. Now, I think till this part, it's clear. If anybody has a doubt, please let me know. Okay, I think there is no question. Yeah, tell me, Ramji.
The output frequency will change or it will remain the same?
Now, see, so yeah, if you look at the figure itself, the final output will have the same omega 0 and minus omega 0. The scale is the only thing that is changing. So in that case, the frequency will not change. So basically, y of t will be some let's say some arbitrary c. Ramji, you can mute your audio. Thank you. Now it will be some sine omega 0 t. The c is some arbitrary, not arbitrary, but something that actually depends on this Gaussian function. But it's not necessary that you compute it during the interview. Okay, now you got this. Another sub question from this observation. What can you say about this so-called Gaussian kernel filter? What kind of filter is this? Can somebody reply?
Low pass.
Okay, so next question is, yeah, why is it a low pass filter?
Okay, low frequencies are passed and high frequencies it's cut off.
I mean, that is what definition of a low pass filter is, but why do you think this situation is causing that? I mean, this all these is making it a low pass filter. One basic way to look at it is like you can look at the frequency domain. Yeah, continue. Anybody? I'm hearing some
magnitude was decreasing exponentially with frequency.
Yes. So that is one, like a good way of saying that, like for as a, the next answer to the same question. So one way of answering is that if you look at the frequency domain spectrum, you can see that the magnitudes go down as the frequency increases. But another way of saying is that given a pure sinusoidal signal, when I pass it through this, through this system, the amplitude of the sinusoid will go down as the frequency increases. That is what we have proved right here itself. Like this one itself proves that. Now, why does it apply to any kind of signal? Okay, given some arbitrary signal, why does the fact that a single sinusoid has this effect can cause an effect on some other complex signal? This is because any signal, any kind of real signal can be, can be considered as a combination of multiple sines and cosines. Now, if you think about the linearity property, always think in terms of properties. So if you think about linearity property, we can say that this summation of multiple sinusoids is one signal. And if you pass it through this, you get another summation of multiple signals where the lower frequency signals have a higher amplitude and the higher frequency signals have a lower amplitude. So automatically the output of any complex, not complex, any real life signal when passed through this Gaussian function will be a low pass filtered, meaning a lower, it will not have high frequency details. So that is that is the sub question. All right, now next the another sub question that they might ask is what would happen if you multiply in time domain. Okay, so this might be a little related to the sampling theory that Prashop discussed earlier. It's not related, but the way you can solve it will be a little related. Now, in what would you do if you are multiplying this in the time domain, meaning you have a sinusoidal signal, something of the sort, you multiply it with another Gaussian. This is happening in the time domain. What will the output of the frequency response look like? Can someone try to reason that? What will be this frequency domain output response look like?
I think it's still sinusoidal.
That will be in the now what Karthik said is like sinusoidal. It will be in the time domain. Do you think it will be in the frequency domain? Will it be sinusoidal?
Sir, a shifted Gaussian pulse.
Yeah, two Gaussian pulses on right and left.
Yeah. So Gaussian pulse. See, yeah, Gaussian signals you can call them. Pulse. Okay. Yeah, Gaussian pulses, shifted Gaussian pulses. But they have some phase differences. Okay, it's not always on the, now if I draw the, in the frequency domain, it will look like you have two different Gaussian pulses superimposed. Okay. Sorry.
Yes, sir.
Now why is it so? Because you had two impulses and you convolved, because multiplication in time domain will give you convolution in the frequency domain. You convolve that with a Gaussian. Okay, wait. You convolve that with the Gaussian, you got two different Gaussians on at 2 points. Okay, so this is how you don't need to be so aware about the actual amplitudes or anything. Even phase is not a big deal. Actually, all you need to think about is the magnitude of the spectrum and all those. And finally, this the output will kind of look like. So someone said that it will look like a sinusoid. At the time domain, it will kind of look like a sinusoid that is fading away in two directions, meaning the envelope will look like a Gaussian. That's all. Okay. Okay, so now actually these kinds of concepts are important because Gaussian kernels are useful in multiple applications. Like Gaussian kernels are used in image processing when we need to process the data only near, say you have a image, you have some, like, let's say you have an image, you have an image, you need to process it. Let's say you need to apply some process, you need to apply some sort of operation on a neighboring part of the image. What you do is that you apply a Gaussian filter to only select the path, the pixels nearby, and then you apply some operation. For example, if I apply some averaging operation, the final output that I get will be some kind of, if you do this kind of averaging, the final output will be a blurred version of this image. And this can also be seen in audio processing also, where if you apply some sort of Gaussian filter, the output audio will not have like high frequency details. And maybe in communication, can Prashop, do you have any idea, like any examples in communication you can?
For LT.
Yeah, meaning this patch multiplication thing.
Okay, so So we have this not exactly in communication. So we can have these kind of things in like audio processing and things like that. So there is something known as windowing operation. So some of you might be aware of that. So windowing basically means we take only a certain part of the signal that we see. So now there are different types of windows, like you have your usual rectangular window, then you have this Gaussian window, things like that. So that itself is a different area by itself. I think we need not go into that detail, but yeah. Is there any particular question that you asked that I might have missed? My audio was not clear at my end that time.
Yeah, that's what is related. Yeah, windowing idea.
Yeah.
So that's good. Meaning, so another, I mean, from an application point of view, if you are designing windows, a Gaussian windows give a smooth frequency response. Whereas if you use a rectangular window, the response will be like a sinc function. So sinc function is ranging from -infinity to infinity, and it will cause all kinds of aliasing problem when you are sampling. So all these things can come up, like that's the kind of application that we are looking at. So when the panel is asking some questions, some question, it's mostly because there is some sort of application that is related to this problem. That's why they're asking such questions. They will not be asking some very arbitrary question and very arbitrary equation kind of questions. They'll ask you some intuitive questions where you can, graphically or applying some properties, you can get to the solution. Okay, I think I'm done with my set of questions, and I think time is already 7:30. If there is any more questions from the students, if you have any doubts or in this part, or maybe if you have any other general doubts, please feel free to ask.
Sir.
Yes.
Sir, in PhD and MS or PhD, sir, like we studied in the BTech course curriculum, and in MTech we are also studying the subjects. But sir, in
yes.
MS and PhD, we are stuck to a topic and conducting research over it for 2-3 years to make some innovative idea, innovative application of some thing or any. So, sir, I want to know about the MSR PhD course curriculum type things, what we study over there, and what
Curriculum.
our objectives.
Okay. Yeah. So see,
in BTech we learned the things, and in
yes.
MSR PhD we are researching over some topic like the scientists do. Or
yeah. Right. So see, now MS or PhD, basically you can call both of them as research. Firstly, in IAC, as we may have explained in multiple sessions, that we have this research training program, and it's basically taking courses like maybe for 1 year you will be taking multiple courses on mostly on math and some courses on whatever your topic is. So at that point, you are still learning. I mean, it is called as research training program because you are kind of you're basically trying to improve your skills in those areas. Okay, so at that is one phase of your research where you kind of get to the level of IAC or get to the level of math that you can use in your further research. And the next part is research, which is like research meaning there is some problem that exists. There are some methods that this problem is like some methods that try to solve this problem. And you see that there are some what can I say, some negative points about these problems, like it fails in some cases, and I want to improve that failure cases and make this method much better by trying out multiple ideas, multiple novel ideas, and trying out multiple experiments. So that is a totally different thing. But yeah, initially you have this part where you're training yourself, and by that time you will be at a position where you can read literature easily. You can talk with research oriented people much more with much more rigor. And then you are like, after you are getting all this training, you are able to talk with people. You are able to, do this literature survey, meaning you are reading multiple papers on your topic and trying to find, or even reading totally unrelated papers and getting inspiration from them. So this process is like, it has some level of uncertainty. It's not like course, but as long as you are doing your part, like doing your hard work, you'll get of course, some feedback and some support from your guide and also from your lab mates. All these combined will be your research. You will do research meaning you're coming up with new ideas and all those. So yeah, research is kind of completely different, but at the same time, you're learning. It's not like you're trying out new stuff. You are learning what is out there. You're trying to come up with something else. So that's like a gist of what research would be. And if Prashobh or Shravanti can add to it.
Okay, sir, I understand very well.
You explained very well. Nothing much from my side. It was very nice explanation actually.
Okay. All right. Yeah, you also have a completely different experience. I know you, so if you have anything to add, you can.
Nothing much. I think this is fine.
Okay. Yeah. Any other questions?
One side point, like this last question that Nitin explained regarding this Gaussian and all, like this was asked to me in my interview. So yeah. And I did not answer everything in the first go. Like I did not know what a kernel was. I did not know what is the meaning of Gaussian kernel. So I asked them for like clarification, and they were very helpful. Okay, I think there are some raised hands. Maybe okay.
Hello.
Yes.
Sir, in one of the interviews, I have been asked what is the difference between band limited signal and time limited signal?
Once again,
what is the difference between band limited signal and the time limited signal difference?
Okay. So basically, Nitin, you want to go, or like may I continue?
Yeah, you can continue. Yes.
Yeah, so basically a signal that is having finite bandwidth, or the largest frequency in that signal, if it is finite, then we call that to be a band limited signal. So if you take the Fourier transform and you have a shape where after a given point there is no other frequency component, then we said that is a band limited signal. Now, time limited signal is basically something where the signal exists only for a certain duration of time, like 0 to t, something like that. So, are you from BTech ECE background?
Yes, I'm ECE.
Okay, so you are aware of this BPSK and all these. I mean, like amplitude modulation, these things, right?
Yes.
So in communication, whenever we say the symbol that we transmit, we basically say symbol exists from 0 less than t less than capital T. Like that only we write, no, generally.
Yes, yeah.
So that is an example of a time limited signal. Now, on the other hand, for a band limited signal, the example is the pictures that I drew during explaining sampling theory. Is that okay?
Yeah, okay. So time limited signal means you are talking about the digital signals, binary ones and zeros.
No. Need not be binary, but it exists only for a certain duration of time. Like it won't be for all time. Like 0 less than t less than t, it will be something, and 0 otherwise, something like that. Nitin, can you write this?
So all the digitally modulated signals are time limited signals. Can I say like that?
In general, but even I advise you to just say the basic definition. Like you can say that a signal that is having a finite time duration, that is a time limited signal.
Okay.
Because if you say signal, if you say modulated digitally and all, next question will be from that topic. So yeah.
One more question. I have been asked what is sampling. I told that sampling means multiplying an analog signal with the impulse train. And they asked me to draw the spectrum of the sampled version. Then I have drawn that pulse train modulated with some x of t, like that I have drawn. And they asked her how to reconstruct the signal.
Very good.
And then I told that multiplying that sampled version of impulse train with the sync pulses. Every sample instant we have to multiply on sync pulse. Thereby we can reconstruct. I told her.
Okay.
and they ask what will be the bandwidth of the constructor signal. Can you find like that? They asked. There I got stuck.
Actually, your answer is correct, but there are a few minor issues in that. So first thing is that you told like even general, I think so in general when asked about sampling theorem, it's good to say that sampling. So sampling is the process of converting a continuous time signal to a discrete time signal. So that's the definition of sampling. Now, how do we do sampling? We do sampling by multiplying with an impulse. That's it. That's how it works, right? So when you're asked to define what is sampling, it is good to just say that it's a process of converting to discrete. So rather than saying we're multiplying with the impulse train on a signal, it's good to say we are converting a continuous time signal to a discrete time signal. Now, how are we doing that? We do that by multiplying with an impulse. Correct? No, till now it's okay, right?
Yeah.
Okay.
Understood.
Now, to your second question, how do we reconstruct that? So the reconstruction of this thing can be carried out by something known as sinc interpolation. So even if you don't get the word sinc interpolation or that sinc function at that time, what we can show that is like since that you have already drawn that picture having this like this shape coming at 0, fs2, fs3, fs and that non-overlapping all these things, you can just say that if you multiply that shape with a box function, then you will be essentially getting the required shape back, right?
That is passing the signal into some low pass
filter.
filter.
Low pass filter, exactly. So you're passing a signal into a low pass filter, and then once you do that, you'll be getting the required signal back. Now, now that already answered two things. First is that since you're using a low pass signal and you are getting the signal exactly back, bandwidth will be exactly same as what you started off with. So there will not be any change in the bandwidth before you sample and after you sample. It will be the exact same signal.
Okay.
And second thing is that you also told that what is sinc interpolation. So better way to say is that either you can say that you are multiplying with a box function in the frequency domain, or you can say that you are convolving with a sinc function in the time domain. So it's not that you are multiplying with sinc functions, you are convolving in sinc function. So you're multiplying in the frequency domain. So in the time domain, you are basically convoluting this sample signal with a sinc function. Shifted sinc function, basically. Yeah, that one. That shifting.
There is equation summation n tends to minus infinity plus infinity.
Yeah.
X of t into sinc of t minus nts by ts.
Correct. Something like that. I think some factor I might be.
The shifted version of sinc person.
Yeah, you are basically convoluting the samples with a sinc function. So the result of that convolution is that expression that you have over there. Are you okay? Okay, right?
Yeah, yes, this is one.
Okay.
Sir, I have a question.
Yeah.
Sir, in the interview, they ask a very simple question: sampling, define sampling. So, sir, how do we decide that up to what extent I have to answer the question? As we know many things about sampling. So, just definition converting analog to digital means continuous time to discrete time signal, or to add things by my side as they keep silent. They are sit over there, and I don't understand at what point I have to stop.
Okay. That's something that doesn't have a very definite answer actually, but yeah. So if the definition is clear, I think maybe that should be sufficient. Like if you say that, so if this question was asked to me, I mean, it was not asked, but suppose if this was asked to me in my interview, I would say that sampling is the process by which we convert a continuous time signal to a discrete time signal. So if they're still keeping quiet, then I'll start explaining more details. Suppose xt is my signal and I multiply that with a train of impulse, and I get sample like that. So depending on the scenario.
Sir, this is what I want to ask. So actually, I stop speaking and they are still silent. So I again start answering the question in more detail. That's why I want to confirm. Hello.
What was that?
In the sinc interpolation, what is the bandwidth of the reconstructed signal? Can you know that? That's the question they ask. In the case of the sinc interpolation, what is the bandwidth of the reconstructed signal?
Can you please keep your hand raised so I'll come back to you? I think the other question I didn't completely answer. Like who was, I can't see the names here. So somebody is asking like to what extent we need to answer if this comes up in the interview, right?
I was.
Yeah. You were asking. Yeah, right. So generally for a PhD interviews here, I have not seen them keeping just quite. So yeah, I mean, it was not in IASC before, right? I mean, don't tell me where it is. It's not needed, but it was not in IASC PhD before, right?
Yes, sir.
Okay. Yeah. Generally, like yeah, they are helpful. Like yeah. Yeah, it doesn't mean anything else, but yeah. Yeah, I just told that the interview in IAC are good. It doesn't mean the other place is bad or something like that. So that's why I asked you not to tell the name of the institute. Anyway, I mean, Ramesh was asking the question like the bandwidth of.
It's me, Prasad. It's me. What is the bandwidth of?
Okay. Yeah, bandwidth of what? The final answer.
That reconstructed using a sync interpolation. What is the bandwidth? Whether it will be same as the original signal or it will be different.
Exactly same. Exactly same. It's exactly same. It's exactly same. Because sampling theorem itself tells that you can perfectly reconstruct the actual signal by doing the sync interpolation. So you'll be essentially getting the same signal back. So same bandwidth. Is that okay?
No, you told two methods. No, one is passing it through a low pass filter, and one more thing is sync interpolation, multiplying the pulses with
these both are the same method actually. So passing it through a low pass filter essentially means you are multiplying with a box function in the frequency domain. You agree, no?
Yeah. Yes.
Yeah. So multiplying with a box function in the frequency domain is same as telling you are convoluting with a sync function in the time domain. It's the same operation. So all these things are same. Like if you say low pass filtering is same as multiplying with a box that you have there. That is also same as you are convoluting with a sync function in the time domain.
Okay. But after some time, they themselves told that reconstructed sync pulse will have the bandwidth of 1 Hz, only 1 Hz.
No. My answer is for the bandwidth of the signal after reconstruction. I did not tell about the bandwidth of the sync function. The bandwidth of the signal after reconstruction is what I answered as same as before.
Okay.
Now, if you're asking about the bandwidth of the sync function, then that is that 1 by t something, 1 by ts or what is it, that one. But again, it's a kind of vague notation to define bandwidth of sync because it's more correct to say the zero crossing points of sync because sync is something that is still infinity. It doesn't make, I mean, what was the, like, can you say the exact question like?
What he asked means if I reconstruct the signal by using that sync interpolation, what you told, whether the original signal and the reconstructed signal will have the same bandwidth or not. That is the original question.
Okay. So let me rephrase the question once and then I'll tell the answer. So if the question is that suppose you do the sampling and you reconstruct the signal x of t from the samples x of n using sync interpolation, then what is the bandwidth of this resulting reconstructed signal? That's the question, right?
Yeah, correct.
Okay.
Yeah.
So an easy answer is that it will be exactly same. Why I told easy? Because if the sync function, that itself doesn't tell what is the bandwidth you take in the frequency domain. Like you could use a different filter there. But if you're asking about a perfectly reconstructed signal x of t, then the bandwidth will be exactly same.
Okay. Thanks, sir.
Now, if you ask about what is the bandwidth that is needed for the sync or like what is the bandwidth of the low pass filter that you want to use, you should use a low pass filter having bandwidth fs by 2. That's the answer for the other question. The red box will cut the x-axis at fs by 2.
Okay. Got it. Yeah.
Okay. Thanks.
Thank you.
Yeah. Did I miss any other question? I think one question was there. I think it was like for transform theory, we had to cover Laplace, Z and Fourier along with f of t and all. Is it? So like I told in the beginning, like these are the basic transform that we need to study. But in addition to just knowing these transforms, we should also know the applications of these transforms like we've seen here. Like what happens when you sample, like what happens for a LTA system, what happens for a filter, something like that. Nitin, maybe do you want to try that filter question or is it sufficient? That DFT sampling business.
Oh, that one. That one, I don't know how much
Maybe
I can help.
I think I think
So
maybe
I'll give you. I'll say the question. I'll ask you to figure out. If you don't get it, you can just go Google it and look at some Stack Overflow websites for the answer. So
Okay.
the question is this. Yeah, I mean we don't
I think
have
we
time
already
for.
exceeded our time. I think it's like more than 2 hours. I think so.
All right. So the question is this. So let's say you have an endpoint. Okay, I'll show it in the. Let's say you have an endpoint discrete signal. For example, let's say this is like a 6-point signal. Okay, 0 to 5. You apply 6-point DFT. Oh, let's make it a little more general. 8-point DFT. So this is 7. You apply 8-point. 8-point DFT on this signal. You get some frequency response. Okay. Some sort of general kind of frequency response, which is of size 8. 2, 3, 4. Okay, you get some frequency response of size 8. Now, let's say I add some zeros into this mix. Okay, the same thing, same signals only. And I add 8 more zeros into the same signal and compute a 16-point DFT. What will the final frequency output look like? Okay, this part, what will it look like? Will it be 0 padded like as I did in that time domain, or will it be a totally different one? What will it look like? This is the question. So if you get time, try to think about it, and maybe you can use equations, but it's mostly about understanding how it works. Okay, so yeah, if anybody understands the question and if they know the answer, please feel free to say it out loud. Anybody? I think it's a very involved question, but yeah.
So this is actually a standard question. Like it's
Can we repeat the question?
Go ahead.
Can we repeat the question again?
Okay. Yeah. So let's say you have some x of t, which is like some general signal with 8 points, 8 discrete points, and you find an 8-point DFT to get some frequency response. Okay, so some x of k, and that frequency responses will be of size 7. Now let's say you take the same signal as above, meaning you take the same signal and add 8 zeros into it. Okay, this new signal, let's say it's x1 of t. What will be the frequency response x1 of k in the final version? Now this k thing will be like of size 16. Okay, this 16-point DFT will give you a 16-point output. But what will it look like? What kind of relation will this x1 of k have with x of k?
I think
please continue. Whoever was talking.
Yeah, it's more related to like upsampling. So it's like
So
it's a one sample after 0 and one sample after something like that.
Yeah, it is kind of related. Yeah, but I mean it's a little more involved. You can just check. It's not. You can't just say upsampling in this as an answer.
Like reverse of an upsampling, but it's a duality of the upsampling.
I'm also not clear with what you mean by upsampling. It has something to do with upsampling, meaning you're saying that you're adding more points, right?
Like and adding more points will generally give a frequency response like in the left side. So left side should give an upsampling in the frequencies.
Yes, upsampling, or you can say that you get more samples which represents multiple frequencies. Okay. So one thing as a hint, I'll tell that what do these, or you can do it by yourself. What do these points represent? Each of these points. What kind of frequency does each of this point represent? you should think about it. Okay. So each, so let's say this 0, 1, 2, 3. This is the discrete symbol, but actual frequency that this part, or this amplitude represents is the f is actually fs by 8, the sampling frequency by 8, and its multiples are like 2fs by 8, 3fs by 8, like that. Okay, finally you get 7fs by 8. Now, when you look at the same thing in the 16-point DFT, what you get is like fs by 16, then you get fs by 8. Okay, something like this. So this is related to how many frequencies are being represented in the frequency domain. I'll not go too much deep into it. You can try to figure it out yourself. Okay.
Hello.
Yes.
I am not sure, but will it be like a copied version of the 8-point FFT to the left, end up like that?
Copied version of the 8-point. See, whatever you have on the left is the time signal.
No.
But you're talking about this one only.
We have a 8DFT response. Like
yes.
the 8DFT response will be copied. 8-point and 8-point.
Okay, meaning from 7, it gets copied to 7 itself.
Yes.
Okay, then what?
I don't know, but I have some like I remember some like something like that. Like if this kind of thing happens, generally like if we like do some zero padding, then it will be like in frequency domain, it will be like a copy. And in frequency
It
domain,
will be a copy, but yeah, there is something related to this copy thing, but actually it won't be, the 7 won't go to 7 actually. It will go to some other place. And if you look at the frequencies, you will get the idea. So see, this is fs by 8. This one, the second sample is fs by 8. So now you will get the idea. So 1 is being copied to 2. Okay, that's so like basically you will have more resolution. Like you will have more information in between. Not resolution in like literal resolution, but you'll have more information in between added up. Meaning this is called this will be interpolated, this final signal. Okay, meaning this 2 will go to 4, 3 will go to 6, and 7 will go to 14. And finally, you'll have one more sample for 15. So basically, this envelope of this final signal will be maintained along the entire region of the frequency spectrum. Okay, now this question is a little too much involved. I don't think someone is going to ask this, but yeah, this is a kind of question that is too much to ask. So don't be worried about this question. Anybody have any doubts or any other questions? Yeah, there are a lot of raised hands. Ashok has you have 2 raised hands.
Hi. Actually, I have a small thing to add. Like, sorry to interrupt. So this thing, so they just want to check how you think at that time. Like, they want to see are you really answering by thinking or just recollecting something from your memory and just directly telling the answer. So even if you don't answer this question completely, that is perfectly fine. But if you see this question without even thinking twice, if you say, okay, this is oversampling, then they might ask, okay, what is oversampling? That's the purpose of asking this question. It's not a very simple question. They also know that. They just want to see how you think at that time. They don't want you guys to recollect something from past and then say the answer.
That is the thing. Actually, I remembered something like a theorem that if you do zero padding in time domain, it will be like the frequency domain. It will be like copied and copied, like how many zeros you are adding that way. But I think it is not like that. It is different thing.
So actually, I think you might be telling about I have one more comment. Actually, this is not usually what is known as upsampling. So there is something known as upsampling in DSP. So this is not exactly upsampling. Here you are just adding more zeros at the end and you are getting a longer sequence.
Normally
But
it will be add
upsampling
zeros
in
at the
between,
sample end.
Upsampling will be usually done by adding a 0 in between the non-zero points. So it will be like a 0 will be there, then next point will be 0, the next point will be something non-zero, like that the upsampling happens. Now, if you do upsampling like that in the Fourier domain, I think you will get copies of the same thing. But here you are not doing that.
Yeah, so this one is in some other sense, this one is a different kind of I don't think if you can call it upsampling. This is interpolation with with upsampling.
Kind of, yes.
Yeah. Interpolation plus.
And the other thing, like it's also don't get carried away by this 7fs by 8 and all. I mean, that is not the main thing. The main thing is that you get like a same shape, but basically, if you answer that, okay, let me tell what is the wrong answer. So if you say that if you add 8 zeros in the time domain, you also get 8 zeros in the frequency domain, then that's the wrong answer. That is mostly what they're expecting. So unless you tell that answer is still okay. If you just put 8 zeros here, you don't get 8 zeros there. So that's not the thing. And this number, I think like this fs by 8 and all, I mean that people use different notation. Like somewhere you might see fs by 16 in the first graph itself. So that's not the point. Like it just.
Yeah, that's right.
Yeah,
I
so
went a little too far.
Yes. So it might be that number might be different. Different people define this fs itself in different ways. So we don't know. So instead of memorizing fs by 8, it's better to kind of see that, okay, like at least you should be saying that you don't get 8 more zeros there. So. And why did I tell that? Because Fourier transform, as you know, this DFT is each DFT is a function of all the points, not just a single point. So x of k is what? Summation over n, x of n e power minus j 2 pi by n k. So each sample itself, each DFT point itself is a function of all the time domain points. So you don't get just 8 zeros like that. So this fs by 8, I mean, don't get carried away by that. Yeah, some textbook use fs by 16 there, some use like fs. We don't know how they want to interpret.
Okay.
Yeah, I think maybe you can erase that. I think that number might be a problem because if you get carried away by that number, it's a problem. Yeah, I think it's you need not think about fs at all. Like you can just say that, okay, you get more points, but then yeah, something like that. But yeah, this is a tough question. This is a tough question. Generally, this much is not asked. Yeah. But there will be somebody who will just directly tell without thinking. So they want to see if you are memorizing or not. They just want to see if you're memorizing and telling, or are you really telling by knowing the stuff. Don't get worried about this. Like this is a very hard question. We didn't solve, so it's okay.
Yeah.
And we are still here, so it's okay. Yeah.
Okay. Yeah, there are more raised hands. Now, Dibyanchal.
Yeah. Hello, sir. Am I audible?
Yes.
Yes, sir. So I got an interview call from Sense and DAC department as well. So will they also follow the same interview procedure, or they will ask a question related to their domain?
Yeah, so I mean, I think Prashok has gone for the interview of electrical and EC, and yeah, you can say that, Prashok, like you have found that difference, right?
So
yeah,
I'm audible, right?
Yes.
Right. Yes. Yeah, continue, Prashok.
Yeah, I think my net was a bit, but yeah. So you're asking about the interview in Sense and electrical, right?
Yes, sir. DESE department.
Oh, sorry, DESE and did you say Sense anywhere?
Yeah, Sense and DESE, sir. DESC.
DSC and what's the other department?
Sense, sir. Center for Nanoscience.
Okay, that I have no idea. I have absolutely no idea about Sense. DSC, I myself have not attended, but I had attended their MTech interview. So. So again, like depends on what area you choose. Like if you go for some embedded systems or things like that, I think it might be different. I don't know. And we are not the right people to comment on that. Like we know only about the thing in EC department. Electrical, I can tell. Electrical, like if you go for interview, they also generally ask us to pick a topic where they sometimes ask transforms and linear algebra, things like that.
Okay, sir. So like I am from optoelectronics and laser technology background. So will they ask if I choose a transform theory as my topic? So will they ask these DFT, those kind of things, or they will just stick to basics of transform theory like LTI system and sampling theory, all those things?
Are you asking about ECE or are you asking about other departments?
ECE, sir.
Okay, so in ECE, like actually, it might be a good idea to check with so tomorrow there's a session, I think, on I don't know the exact topic, but it has to do with this photonics and areas like that. So it might be good to ask them because generally the policy or like what we generally suggest is that for people going for communication and signal processing, this is very important. So we are not very sure how important this is for those topics. So in that case, I don't know, maybe they'll ask more theory, but actually we are not the people. I think none of us are from that area, so we can't really answer. We can only tell about signal processing and communication right now.
Okay.
But be given, so assuming that that's there, but like suppose if you choose this topic, then I don't know, like they might ask, but should you choose this topic, that you have to first confirm with the others. Like I have heard that the calculus is also needed for those areas. I'm not very sure. You please check.
Yeah, okay, sir. And
Okay.
sir, one more question.
Yeah.
Can they will ask questions from our final year MTech thesis?
So generally, it all depends on the specific interview panel and how the interview goes till that time. Nothing can be confirmed. Generally, they will start with math topic. So at the end, or even like they might start with the project, but the emphasis will be more on the math topic. Now, suppose that you are appearing for interview and one of the you are planning to work on the same topic that you worked during your BTech, and suppose one of the panel members is your potential advisor, like you want to work with him or her. In that case, they might ask more questions pertaining to your project. But yeah, anything can be expected, but more focus should be on the math, at least for communication signal processing.
Okay, sir. Thank you, sir.
Yeah, thanks. Yeah. Saumyadi.
Yeah, hello.
Yeah.
Very good evening.
Yeah, good
so,
evening.
my is not actually mostly technical. I have questions about the research topics and all. So, actually, I have been offered. I have been given a offer letter for interview for MS in electrical and ECE department both. So, as you were mentioning right now that maths topics they ask, like in my mail also they mentioned topics like linear algebra, discrete mathematics, probability theory. They are gonna focus on this part. So I was asking that I actually wanted to pursue something, some topics based on machine learning and artificial intelligence as such, but as I do not have such great score, I couldn't apply to that. But now when I was applying for that MS in EC for the while filling up the Google form, I saw many professors had specifically those research interest and research problems based on computer vision, NLP, reinforcement learning, and all. So I was just asking, would it be okay if I fill out those prompts as I'm interested in working on those areas? But currently, to be honest, I don't have deep knowledge on that because it's a recent current topic like the artificial intelligence, and my background is electrical.
Okay.
So could you guide me
I
on
think
that?
like for the EC department, I think if you're interested in those areas, you can choose that, is what I feel. Maybe during the interview they might ask, and the main thing you need to be concerned about is like which area exactly you want to work on. So you have to read through the description each faculty does. So why I told is because like when you say you want to work on machine learning or artificial intelligence, there could be multiple applications. Suppose if you want to work on machine learning for artificial intelligence for natural language processing, I don't know like who is the right faculty for that in EC department. There might be somebody, I'm not sure. If you want to work on machine learning for wireless communication, that's a different faculty. And you won't find people working on machine learning for communication electrical, that's sure. But also like if you want to work on audio or like things like that, machine learning for audio or like things like that, then there might be more people in electrical. So you have to see like which department you actually want to go. That's the main thing, like that you have to see. And regarding your interest, you can tell that actually. I don't think it's a problem. Like, Nitin, can you like, is that the thing like you want to add anything?
Right. Yeah, not much to add, but yeah, so interest you anyway mention. Of course, you need to go through all these who you are like potentially going to work with. Look, you need to go through all this. It's your future, so you need to, especially like multiple times. I think here the professors have mentioned that you need to go through the websites of each faculty, go through their work and everything, and try to like sum up some topics or some faculties who are working on the topics in which you are interested, not very much broadly in machine learning. See, machine learning itself for someone for me personally, image processing machine learning, that is something that I like, but communication for machine learning is something that I don't like. So machine learning broadly has a lot of things. So you need to focus a little bit more. More you focus, you'll get there much better, easier. So you better go through these faculty information, and maybe, I mean, even better if it will be even better if you go through their what they are working on, their current recent publications and all those. Like, don't have to read the whole paper, but go through their topics and all those.
Okay.
Think,
And another thing,
one more thing from my side, like I don't know to what extent this will be effective. Like if you're already sure that you want to work on a single area, it is also possible to contact some of the students in their lab. So if possible, like I'm not sure will they respond or anything like that, but if you get a chance, speak with them also. Like if you just had, like Nitin told, like it's 5 years of your life, so you have to be very careful on, because you should not end up in the wrong area. Like for example, if suppose you want to work on machine learning for communication and then you join electrical department, there won't be anybody there working on machine learning for communication. So yeah, is that okay?
Actually, I was actually wanting to ask on that topic, that something that you told, that machine learning on wireless application and machine learning, and specifically on topics like natural language processing or other things like that. I need to mention that, or I need to explicitly tell those professors or show my interest. Like, to be honest, I do not have such deep knowledge to confirm that which topic I want to work upon. So actually, I wanted to ask that whether in MS only do they ask so much that which specifically in which research topic I want to work or not, because some of my friends had appeared for MTech AI. So I guess they have some screening test and programming programming languages and such data structures test, and they had an interview. Like my senior told, they had an interview on mostly on mathematics part, like the theory part, linear algebra. So is it basically in those MS program only they delve deep that which topic I wanna explore in machine learning also? So
okay,
is it only MS PhD or is it in MTech also? MTech also, like we have to explain that which specifically which subtopic we want to explore.
Okay, so to answer that, like the regular MTech program that we have here, like the MTech KA or MTech SP, so that will be coming through GATE, right? You'll be shortlisted based on GATE, and then you'll be having the interviews for that. MTech, not the MS, MTech Research, MTech. So for MTech programs, they generally don't ask too many things. So how it works is like you join here, you will be assigned a faculty advisor. After I think 1 semester, I think you have to choose your actual gig. So till that time, you have the complete flexibility to change the area, all those things, if you're going for MTech course program. Now, if you're coming for MTech research or PhD, that from the day one you come to the campus, you will be assigned the advisor, and that advisor cannot change later on. So that's the main difference between MTech and MTech research. So for MTech, so even though like you told, your friends might not have got much questions regarding what area they want to work on, they might ask in the PhD or MTech research. So when I appeared for my interview, they asked me like what area I want to work on. So I was not very clear. I was not very clear on what I want to work on. So I just told them that. So that is also an acceptable answer. Like we need not know what we want to do at that time itself. So I told in a broad way, like I want to work on signal processing and communication. Like that I told. I did not tell exactly what I want to work on. So that should be okay, I think. Yeah. But if you have interest in machine learning for communication, they might ask like what kind of machine learning, because that's a very valid question. Because we can also, I think, yeah, to give you a sense of the difference between the work. I mean, like, so I personally work on machine learning for wireless communication, and Nitin works on machine learning for video. We can't read each other's papers, so it's that different. So yeah. So
yeah,
things are different.
Oh.
Yeah. You agree with that, right, Nitin?
Yeah, very much. Yeah. Okay. I think like Soumyadeep, you got the answer.
Yeah. Thanks.
Yeah, thank you. And Sanu Roy has raised your hand.
Yes, sir. My question is about the all-pass filter. Like in all pass filter, we pass the all or allow the all the frequency of the signal. I know that the impedance matching are required to pass a signal or like in a system. I want to know more about that, if anything more.
Actually, can you repeat that question? Like I couldn't completely hear that actually. Like you all pass filter, right?
Yes, sir. About the all pass filter, we know the in all pass filter we pass or allow the all the frequency of a signal.
Okay.
And I only know the part of the impedance matching and the phase shifting of the filter, like in a system to another system. I want to know more, like there are some anything like practical thing about the all pass filter, like practical aspects.
Okay, that even I'm not very sure. Like right now, I'm not sure. Like the example that you already told is what is coming to my mind, like how to adjust the phases. But yeah. So by definition, an all-pass filter won't have any change in the frequency response, but the phase response can be different. So for adjusting phases, maybe you can use, but I'm not aware of any application. Like maybe Nitin or Sravanti, you want to add something?
Nothing here also, other than changing phases. Yeah, I'm also not person to answer that.
Yeah, I think we are not working on that area. Maybe circuit people can help better. I'm not sure.
Okay, sir.
Yeah. Okay. Thanks. Any other question? We might have missed some questions that are typed in the chat. So if any of you feel that any question is not answered, like please raise your hand and you can speak now, I think, because we kind of lost track of till what extent we answered. Anything?
Yeah, hello. Sorry to disturb you again. Will
problem,
this
no problem.
interaction be posted on YouTube or any other wherever we can get? Actually, I joined a bit late. That's
Okay.
why I was.
It will be there on department website.
Okay. Can you share the name of the channel on the chat?
Not channel, but it's on our website, like ECE department website. Let me see.
Okay. I
think you will be able to find it there, I think.
I think someone has shared some link in that.
Oh, is it?
In the chat.
So there is one page where you get the information about the interview, right? Like the one that tells that you need to choose these math topics and all. The same page bottom, it is there. I mean, till today is yet to upload, but yeah. If you see, you can get there. I think I'm not able to.
The ECE prospective students link is, I can see some link. Yeah. So yeah, reposted.
Yeah.
Yeah. Right. Yeah. Thanks.
Thanks. Yeah, totally. Any other question? Any other question?
Hello, sir.
Ranji, yeah.
Sir, I have got interview call letter from electrical engineering department. So how to
sorry, once again, like my net is bad. Can you say once again?
Sir, I have got interview call letter from electrical engineering department. So which topics to prepare for interview? Please tell me.
Electrical.
Yes, sir.
Nitin, can you hear it correctly? I mean, I'm getting some echoes. I'm not very clearly hearing.
Yeah. So he asked what to prepare for electrical engineering department interviews.
Okay, that one actually.
Yeah. See, again, this is a session from ECE. We are given some briefings about what topics to prepare on ECE interviews only. We don't know anything very clear about EE. Maybe they might be conducting some other sessions or something. Okay, so yeah, we are not like the right people to answer such
yeah, exactly.
questions.
Yeah. Yeah, sorry,
Anybody
but
else?
I think
Yeah,
that's the best we could say from our side for that question.
So, okay, sir. Okay, thank you.
Yeah, thanks. Any other question?
Anybody else? Yeah, technical or non-technical, anything you can ask.
Yeah. No questions, I guess. Did we miss anything from the chat? I don't remember actually.
Hello, sir.
Yes, please.
Hello, sir.
Yes.
Is this I'm audible?
Yeah, you're audible.
Sir, there is a simple question. I am interested in MTech research. So I think after completion of my MTech research, where I am, I think I want a simple question. Where I am, I think I am completed BTech. So after I completed my MTech research, where I'm in terms of knowledge, if I'm talking, or in terms of placement, if I'm talking.
Okay.
Is this my question is clear?
Actually, I mean, like some audio issues. I'm not sure if it's only me or like Nitin. Can you were you able to hear it correctly? I think I have some issues here right now.
Yeah. So what he asked is after completing MTech research, what is the kind of expected knowledge level that he would have? At what point will he be in terms of placement and all those? That's what he asked.
Yes,
okay,
exactly.
So there I think generally for placements, I don't think they do much distinction between MTech and MTech research. So in terms of knowledge, how it happens is like when you do an MTech research, that is like it's a proper research program. You'll be working on a single topic, and you'll be, I mean, not single, but you'll be having a very focused area, and you come up with your own new result, and you submit your thesis. Then only you can graduate with MTech research. On the other hand, for MTech program, it's a 2-year program. So first year you will be doing coursework. Second year also somewhat like few 2-3 courses will be there. Then you will work on a project with one of the faculties, and that project will be the thing. So in terms of the courses that you learn, you will be taking more courses in the regular MTech program. So if you see that wideness of the spectrum of the courses that you have, then MTech will be having more idea. But for MTech research, you will be having more knowledge about the thing that you worked on. And regarding placement, I think I'm not the right person to answer, but yeah, Nitin, maybe you can add something.
Yeah, MTech research. See, MTech research. One takes this MTech research course because they're interested in research, more interested in the research side than the other part. But anyway, if you're interested in, I think any MTech or MTech research students are allowed to go for the interviews and all those. There is nothing stopping them. I mean, placement-wise, anyway, it's expected that MTech research students are interested in research. And just like Prashov said it very clearly, what you are aware is in MTech research, you're aware more about a specific problem, while MTech, you're aware about more, wider area of topics. That's all. I mean, not as wide as BTech, but wider area of a specific topic. So we can't say much about the placement opportunities, but yeah, to my knowledge, most of the MTech research students who were interested in job, so most of the friends that I knew have got placed in good places, but I can't assure you anything right now. Maybe there will be other sessions regarding placements you can join after you're joining the institute. Did that answer the question? I mean, or maybe at least partially.
Okay, sir. Fine. Fine, sir. Thanks.
Okay.
Thank you.
Thanks. Any other question? Any other question from anyone?
Sir, there is one more question from my side. I think it is just like a stupid question. But I have
some question is stupid.
think I have some fear of MTech research. I don't know why. I think some people are saying about the in MTech research, it's way longer than MTech, and yeah, it's good. I think it's way longer. If you're getting a good knowledge from MTech research, it's a good thing.
Yeah.
I think there is a lots of the pressure in mindset when we doing MTech research. So I think how I really don't know about properly exact how it MTech research is gone. Just I have a little bit about fear. So I think I just want to. So what is going on that means that the burden in your head is going on well after I am come inside the MTech research. So if this I handle it properly, that's question I have in my mind.
Okay.
Yeah, I can handle it or not. Yeah. That question.
So yeah. So Nitin, yes, please.
Yeah, sure. See, I mean, we like if you look at us, we have look at Prashov. He has gone through 4 years. Look at me. I have gone through 3 years. I think MTech in average it will be in average more than take more time than MTech. And that's because you need some more time to focus on that specific research topic, and you might be able to even like come up with some really good papers and contributions to that specific field. But see, this thinking about a burden into your head is one thing is, yeah, you are focusing on a specific problem, you're trying to solve something, and there will be times when it doesn't work out. Like you try something out and it's still not improving beyond what is expected. So not expected meaning, let's say there is some method that's out there, you're trying to improve your work beyond that that existing method. There might be times when it's like it does take time, so you need to take time into account. Like you don't need to feel pressurized. It will take some time to go through this to understand the situation and try out multiple things. But in my opinion, as long as you kind of do your hard work and try to be always always solve the problem. Like if you try your best to solve the problem and just don't stop solving it, that's the thing. Like there will be times when you wait for 2 months, you try some experiments for 2 or 3 months continuously, and still you don't get some result. Doesn't mean that you won't get it forever. It means that you have got a lot of experience in working in the same problem, that intuitively you'll get a better idea of understanding the problem, or maybe coming up with a newer idea. So it's like there is some level of uncertainty, it's true, but the final output is that you are you are able to handle even that level of situation. Like it's about handling things, but like don't feel like if you don't get a problem, or like if you don't get a solution or anything, it doesn't mean that you will not get it forever. Like you are again gaining experience from each and every day. It's not like you're doing this as long, like if you don't get a perfect solution finally, doesn't mean that you haven't learned anything. You are always gaining some experience. Not getting a solution is also part of the experience. Okay, then only you'll get a better solution. So you don't need to worry about it. There are people who are here to help you out. Your guide will help you out, definitely. Like your guide will be there to support you, like point you towards basically what's the meaning of a guide. Is he or she is supposed to guide you to some location. So like these people will guide you in the right direction. They know what's out there, what's possible. Like they have a better knowledge of the current literature, current situation, what's going to happen in like next 5 years or next 10 years. So they will help you out and like in terms of guidance. And of course you will have friends here and there, so don't need to worry about such like issues. Try your level best, go on trying to solve it. Even if you don't get a solution, you'll still continue doing it, and finally with time you will finally get to the place where you are. And don't consider failure as a bad thing. It's always an experience. So don't be afraid of this failure thing, or not able to churn out the expected output or anything. You're going through IAC anyway, so you'll finally get to the point that you are expecting in your head. So don't worry about that. Anything from Prashobh?
No man, very well explained. I don't have anything else to add. Very well explained.
Okay.
Thank you, sir.
Yeah. Yeah. Any other question? Anybody else have any other question? I think it's 8:20 almost. Maybe if we have no questions, then maybe we can wrap this session. Any question, any general question, any technical question, anything else that you might have to ask us? Feel free to ask. I think then, if not, then it's kind of we can wrap up the session. So thank you very much for attending. It was a very good experience for us also. Hope to see most of you in the campus, like our juniors, let's say, and all the best. Just one quick thing, like don't panic in the interview if they ask you some question and if you're not able to answer at that time, it's perfectly fine. You don't have to answer all the questions to get here. I think none of us have answered all the questions correctly. So if you're stuck somewhere, they keep on giving hints to drive you to the correct solution. So be calm and yeah, all the best. Thank you for attending. All the best.
Okay, I'll add something to it. See, this professors are not like, of course, they are experts in this field. They are like world-class experts. That doesn't mean that when you're sitting in front of them, don't be afraid of them. Like they are having a chat with you. You are having a chat with them. They are asking you something. You are trying to figure things out. They'll help you figure things out. Just have a good chat with them. It's a technical discussion. That's all. Don't be afraid of the people, like as they are like the highest level people, but don't feel like that. Always think like you're talking with some people. You're talking with you're kind of having a good discussion with these people. So think it like that, and all the best in your interviews. Hope to see you soon.
Shravanti.
Yeah, I have nothing more to add. All the best, you people. Thank you. Thank you for attending. All the best.
Thank you.
Thank you. Thank you very much. So if there are no questions, we can pause this session.
You can stop the recording.
Thanks. Yeah. Thanks a lot. Thanks for attending. All the best.
Yeah. Thanks for the session. Yeah.
Yeah. I'm stopping the recording.